what you're looking at is a lie. Or, at least, it's not the whole truth. This beautiful, shimmering band of stars we call the Milky Way. It's just a tiny, glowing speck. A delicate, luminous frost on the surface of something infinitely larger and more profound. It's a single, radiant firefly caught in the center of a colossal, invisible structure. A structure so vast that it dwarfs our galaxy, and so mysterious that it makes up almost all of its mass. We're living inside a giant, and for the longest time, we didn't even know it was there. This isn't science fiction. This is the story of our home. Welcome to the Science for Deep Sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. The truth is, our galaxy is a ghost, a whisper of light in an immense ocean of darkness. And the quest to understand this darkness has led us to a revelation that fundamentally changes our place in the cosmos. So, how big is the dark matter around our galaxy, really? The answer will not just surprise you. It'll change the way you see the universe, the night sky, and maybe even yourself. This is the story of how we discovered a giant hiding in plain sight, a cosmic detective story with clues written in the very motion of the stars. The glow you know. The deceptive familiarity of the Milky Way. Let's begin with what we think we know. Imagine stepping outside on a perfectly clear, moonless night, far from the city glare. You look up, and there it is. A celestial river of light, a milky, hazy arc stretching from one horizon to the other. It's one of the most awe-inspiring sights available to the human eye, a vision that has captivated poets, philosophers, and scientists for millennia. This is the Milky Way, our home. From our vantage point, we're looking into the plane of our galaxy's disk, like a bug looking across the surface of a dinner plate. This disk is a sprawling city of stars, a flattened, spinning structure. Standard estimates put the main stellar disk at about 100,000 to 120,000 light-years across. To put that into perspective, if you could travel at the speed of light, the ultimate speed limit of the universe, it would still take you 100,000 years to cross from one side to the other. Within this disk, astronomers estimate there are somewhere between 100 and 400 billion stars. The vast majority of these are dim, red dwarf stars, too faint to be seen from our position. With our naked eye, we can only spot a few thousand individual stars, pinpricks of light against the black. With binoculars or a small telescope, those numbers swell into the millions. But beyond a certain distance, around 10,000 light-years, individual stars blur together, their light merging into that collective, ethereal glow. Our solar system isn't at the center of this cosmic metropolis. We're nestled in a quieter, suburban neighborhood, about 27,000 light-years from the bustling, chaotic core, in a smaller spiral arm known as the Orion Spur. Looking toward the constellation Sagittarius, we're staring into the galaxy's bright, dense central bulge, a region packed with stars, gas, and a supermassive black hole 4 million times the mass of our Sun. All of this, the spiraling arms, the glowing gas clouds, the billions upon billions of stars, feels impossibly vast. It is a structure of almost unimaginable scale and complexity. And yet, all of it, every single star, every nebula, every planet and moon we can see or detect, all of it combined makes up only about 10% of our galaxy's total mass. Some estimates put the visible matter, the stuff we're made of, at just 5%. Think about that for a moment. 90 to 95% of our galaxy is completely missing. It's like looking at a bustling city at night, seeing the brilliant lights of skyscrapers and streets, and being completely unaware of the colossal, invisible mountain on which the entire city is built. The part we see, the part we call the Milky Way, is just the luminous decoration on a much larger, much heavier, and completely invisible entity. This discrepancy, this enormous gap between what we see and what must be there, is the first and most profound clue in our cosmic detective story. It's the strange case that set astronomers on a path to uncovering the true nature of our galactic home. The visible galaxy isn't the main event, it's just the tip of a cosmic iceberg. And the investigation into what lay beneath the surface would begin with a simple, baffling observation. Our galaxy was spinning all wrong. The initial clues. The case of the runaway stars. Every great mystery begins with an anomaly, a piece of evidence that just doesn't fit. For the mystery of the Milky Way's missing mass, that anomaly was found in its spin. To understand why it was so baffling, let's first look at a system we understand perfectly, our own solar system. The Sun sits at the center, holding over 99.8% of the solar system's total mass. Its immense gravity dictates the orbits of everything else. Mercury, the closest planet, whips around the Sun at a blistering 47 kilometers per second. Earth, farther out, cruises at a more leisurely 30 kilometers per second. Neptune, at the distant edge, ambles along at just 5 kilometers per second. This is exactly what we expect. It's called a Keplerian rotation curve. The farther an object is from the central mass, the weaker the gravitational pull, and the slower it orbits. If it moved any faster, it would overcome the Sun's gravity and fly off into interstellar space. This is a fundamental law of gravity, as reliable as the sun rising in the morning. For decades, astronomers assumed that galaxies would behave in the same way. All the visible matter, the stars, gas, and dust, is heavily concentrated in the center. So, just like in our solar system, stars closer to the center should orbit quickly, while stars in the outer regions, far from the bulk of the visible mass, should move much more slowly. If you were to plot their expected speeds on a graph, the line would rise sharply near the center and then drop off steadily as you moved outwards. But when astronomers finally developed the technology to measure this, they found something completely different, something that seemed to defy the laws of physics. In the late 1960s and 1970s, an astronomer named Vera Rubin, working with her colleague Kent Ford, began a series of meticulous observations. Using a new, highly sensitive spectrograph, they could measure the velocity of stars and gas clouds in neighboring spiral galaxies, like Andromeda, with unprecedented accuracy. They pointed their telescope at edge-on spirals, measuring the Doppler shift of the light. Light from the side of the galaxy spinning towards us would be blue-shifted, and light from the side spinning away would be red-shifted. The amount of shift told them precisely how fast things were moving. Night after night, they gathered data, expecting to confirm the familiar Keplerian curve. But that's not what they saw. The results were, in Rubin's own words, puzzling. The rotation curve didn't drop off. It went flat. Stars in the far outer reaches of the galaxies, where the visible light petered out and the gravitational pull from the stars and gas should have been weakening, were moving just as fast as stars much closer to the center. It was as if Neptune were orbiting the Sun at the same speed as Earth. According to everything we knew about gravity and the distribution of matter, these outer stars were moving too fast. They were moving so fast, in fact, that they should have been flung off into the void. The gravity from the visible matter in the galaxy simply wasn't strong enough to hold onto them. Think of it like spinning a weight on a string. The faster you spin it, the more tension you feel in the string. If you spin it too fast, the string breaks, and the weight flies off. In this case, the galaxies were spinning so fast that the string, the gravitational pull of all the visible stars and gas, should have snapped. Yet, the galaxies were perfectly stable. They weren't flying apart. Rubin and Ford observed this phenomenon again and again, in galaxy after galaxy. It was a universal feature of spiral galaxies. The conclusion was inescapable, though initially met with deep skepticism. There had to be more mass. A lot more mass. This mass couldn't be seen, it emitted no light. But it had to be there, its gravity providing the extra string needed to hold these rapidly rotating galaxies together. This unseen substance was dubbed dark matter. The flat rotation curve became the smoking gun. It was the first strong, direct piece of evidence that our understanding of galaxies was fundamentally incomplete. It implied that the visible part of a galaxy was just a small component embedded within a much larger, invisible structure. The true galaxy wasn't the shining disk of stars, but a vast, spherical halo of this mysterious dark matter, extending far beyond the luminous edge. The stars in the outer disk weren't at the edge of the galaxy's gravitational influence, they were still deep within it. The case was no longer just about missing mass, it was about a hidden giant. The next step for cosmic detectives was to find more evidence, to follow the gravitational breadcrumbs this invisible entity left scattered across the universe. The investigation, following the gravitational breadcrumbs. The flat rotation curve was a bombshell, but in science, extraordinary claims require extraordinary evidence. One piece of data, no matter how compelling, is never enough. If this enormous halo of dark matter was real, it couldn't hide completely. Its immense gravity must leave other fingerprints on the cosmos. And so, the investigation broadened. Astronomers began hunting for other signs of its influence, using the universe itself as a giant laboratory. Their next big clue came from an effect predicted by Albert Einstein himself: gravitational lensing. Einstein's theory of general relativity tells us that massive objects warp the fabric of spacetime around them. Imagine a bowling ball placed on a stretched-out rubber sheet. The ball creates a dip, a curve in the sheet. Now, if you roll a marble past the bowling ball, it won't travel in a straight line, it'll follow the curve in the rubber. Light behaves in the same way. When light from a distant object travels past a massive object, like a galaxy or a cluster of galaxies, its path is bent. This effect is called gravitational lensing. Under the right conditions, this bending of light can act just like a lens, magnifying and distorting the image of the background object. Sometimes, it creates multiple images of the same distant galaxy or smears its light into strange arcs and rings, known as Einstein rings. These cosmic mirages are not just beautiful, they are incredibly powerful tools. By measuring the degree of distortion, astronomers can work backward and calculate the mass of the lensing object, the object in the foreground that is bending the light. It's like weighing the bowling ball just by observing how a marble rolls past it. When astronomers started using gravitational lensing to weigh galaxy clusters, they found the same shocking result that Vera Rubin had found with rotation curves. The mass required to produce the observed lensing effects was immense, far greater than the mass of all the visible galaxies within the cluster. In fact, the visible matter accounted for only a tiny fraction of the total mass. The rest had to be dark matter. These observations allowed scientists to create maps of where the dark matter was. They could see the unseeable by mapping its gravitational influence. These maps revealed vast, sprawling clouds of dark matter enveloping the clusters, with the luminous galaxies looking like mere sprinkles on a colossal, invisible cake. The evidence was clear: dark matter wasn't just in our own Milky Way, it was the dominant component of mass on the largest scales of the universe. But there was still more evidence to be found. Another clue came from the impossibly hot gas that fills the spaces between galaxies in clusters. Through X-ray telescopes, astronomers can observe vast clouds of gas with temperatures soaring to millions of degrees. At these temperatures, the gas particles are moving at incredible speeds. Just like the stars in the outer parts of a galaxy, this gas should have boiled off and escaped the cluster's gravitational pull long ago. The fact that it's still there means there must be a tremendous amount of gravity holding it in place. Once again, when astronomers calculated the mass required to contain this superheated gas, they found it was 5 to 10 times more than the mass of all the stars in all the galaxies of the cluster combined. The numbers consistently pointed to the same conclusion: the universe was dominated by an invisible substance. The final, and perhaps most profound, line of evidence comes from the very beginning of the universe, the cosmic microwave background, CMB. The CMB is the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. It's an almost perfectly uniform sea of radiation, but it contains minuscule temperature fluctuations, tiny ripples that were the seeds of all future structure. When scientists ran computer simulations of how the universe evolved, they discovered something crucial. The gravity from ordinary matter alone wasn't strong enough to take those tiny ripples in the CMB and grow them into the vast galaxies and galaxy clusters we see today in the 13.8 billion years since the Big Bang. The simulations just couldn't form galaxies fast enough. However, if they added a massive amount of slow-moving, non-interactive dark matter into the simulation, everything clicked into place. In this model, the dark matter began to clump together gravitationally long before ordinary matter could. It created vast, gravitational wells, or halos. Ordinary matter, the gas that would eventually form stars, was then pulled into these pre-existing dark matter scaffolds. The dark matter acted as a cosmic skeleton, providing the framework upon which the visible universe could be built. Without it, we wouldn't be here. The galaxies, the stars, the planets, none of it would have had time to form. From the spin of a single galaxy to the bending of light across the cosmos, to the very blueprint of the universe itself, every clue pointed to the same culprit. The case was closed. Dark matter was real. The next question was, just how big was the monster we had uncovered? We've followed the clues and built the case for this invisible giant. If this journey into the cosmic unknown is sparking your curiosity, do me a favor and hit that subscribe button and turn on notifications. Because we are about to pull back the curtain and reveal the true, mind-boggling scale of the dark matter halo around our own galaxy. You are not going to want to miss this reveal. The big reveal, unmasking the dark matter halo. For decades, we've been cosmic detectives, gathering clues from the edges of the universe. We've seen how stars move too fast, how light bends impossibly, and how galaxies couldn't have formed without an invisible helping hand. All these threads of evidence weave together to tell one story: our galaxy is not what it seems. Now, it's time for the big reveal. It's time to finally answer the question: how big is the dark matter around our galaxy, really? Prepare yourself, because the numbers are staggering, almost to the point of being incomprehensible. Let's start with the familiar.
The visible disk of the Milky Way, the part with the stars, the gas, the dust, the part we call home, is about 100,000 light-years across. The dark matter halo, this vast cloud of invisible matter, completely envelops this bright disk and extends to an almost unbelievable distance. Current estimates, pieced together from the motions of distant globular clusters and satellite galaxies, suggest the entire structure we call the Milky Way reaches a diameter of nearly 2 million light-years. Let that sink in. The structure we belong to is 20 times larger than we thought. Let's try an analogy. Imagine the visible Milky Way disk is the size of a standard dinner plate. On this scale, our solar system would be a single grain of salt. The dark matter halo, in this analogy, would be a space more than 200 feet across, the size of a multi-story building, with the dinner plate sitting right in the middle. The glowing galaxy we see at night is nothing more than a tiny, decorative centerpiece inside a colossal, invisible cathedral. And it's not even a simple sphere. Recent data from space telescopes like Gaia show the halo is actually squashed into an oblong, or triaxial, shape, and it's tilted, oriented almost perpendicular to the flat plane of the starry disk. This weird shape is likely the result of ancient galactic mergers and collisions. Even more astounding is the mass. The visible, or baryonic, matter in our galaxy adds up to about 100 billion times the mass of our Sun. The dark matter halo, however, weighs in at an estimated 1 to 2 trillion solar masses. That means for every 1 pound of normal matter, the stuff that makes you, me, the Earth, and the stars, there are at least 10, and perhaps up to 30, pounds of dark matter. Our galaxy is about 90% dark matter. This discovery fundamentally redefines what a galaxy is. A galaxy is not a collection of stars. A galaxy is a massive halo of dark matter. The stars are just a bit of luminous contamination, a beautiful, brilliant side effect that happens when a small amount of gas cools and collapses at the very center of this enormous dark structure. Even the classic, flat, rotation curve that started it all is being refined. New data shows that in the far outer halo, the curve actually starts to decline slightly, which is helping scientists build more accurate models of how dense the dark matter is. We are adrift in this immense, invisible ocean. Every second, billions of dark matter particles are streaming through your body, through the Earth, through everything you see, and we feel nothing. They are ghosts in our own machine. The total gravitational pull you feel isn't just from the Earth. A tiny fraction of it is from this gargantuan halo we are all embedded within. This is a profound shift in perspective. When you look up at the Milky Way, you are not looking at our galaxy. You are looking into a tiny, glowing part of it from deep within its true, invisible structure. It's like being a deep-sea fish that spends its entire life at the bottom of the ocean, seeing only the bioluminescent creatures around it, and having no concept of the vast, dark body of water that extends for miles above its head. For most of human history, that was us. But now, we've finally looked up. We've measured the pressure, we've followed the currents, and we've finally begun to comprehend the sheer, crushing scale of the ocean we call home. The Milky Way isn't a river of stars. It's an empire of darkness, decorated with a few glittering lights. The implications: a universe built on an invisible scaffolding. Discovering the true size and shape of our galaxy's dark matter halo is more than just mind-bending cosmic trivia. It's a revelation that completely alters our understanding of how the universe works and how we came to be. First and foremost, the dark matter halo is the sole reason our galaxy exists in its present form. Without it, there would be no Milky Way. As Vera Rubin's work showed, the outer stars are moving so quickly that the gravity of the visible disk alone is completely insufficient to hold them in orbit. Without the immense, stabilizing gravity of the dark matter halo, our galaxy would have unraveled billions of years ago. The stars would have been flung out into the cold, empty space between galaxies, and the beautiful spiral structure we see would have never been maintained. The halo acts as a gravitational glue, a cosmic scaffold holding everything together. But its role is even more fundamental. As we touched on earlier, dark matter was the master architect of the universe. In the fiery aftermath of the Big Bang, the universe was a nearly uniform soup of particles and energy. Because dark matter doesn't interact with light or radiation, it was free to begin collapsing under its own gravity much earlier than normal matter. It formed vast, invisible clumps, the primordial dark matter halos. These halos became the gravitational templates for everything that would follow. Imagine them as invisible cities, pre-built and waiting for inhabitants. As the universe expanded and cooled, ordinary matter, mostly hydrogen and helium gas, was irresistibly drawn towards the deepest gravitational wells. It flowed into the hearts of these waiting dark matter halos, where it was compressed, cooled, and eventually ignited into the first stars and galaxies. So, when you look at a galaxy, you're seeing the successful colonization of a dark matter halo by ordinary matter. This has a direct implication for our own existence. The formation of the Milky Way, the the birth of our Sun, and the creation of Earth were all dependent on our local neighborhood having a sufficiently massive dark matter halo to capture the necessary gas. We owe our existence to a substance we cannot see, touch, or comprehend. This discovery also changes how we view our galactic neighborhood. The Milky Way isn't an island universe. In fact, recent discoveries suggest it's embedded within a giant, cosmic sheet of dark matter that stretches for tens of millions of light years. This massive, flattened structure contains not only our galaxy but also our neighbors in the local group. This means the halos of the Milky Way and Andromeda are already blending into this larger structure. We are not just two separate disks of stars hurtling towards each other for an eventual collision in about 4-5 billion years. We are two massive dark matter empires already beginning to merge and interact within an even larger empire. The dance has already begun. The scale of this dark matter structure forces us to be humble. It reminds us that what we perceive with our senses is a minuscule and often misleading fraction of reality. We have built our entire understanding of the world on the 5% of the universe that is made of ordinary matter. Now, we are faced with the monumental task of understanding the other 95%. The unsolved mysteries. The hunt for the ghost particle. We've unmasked the giant. We've measured its colossal size and weighed its incredible mass. We've understood its critical role as the architect and protector of our galaxy. We know what it does, and we know where it is. But a huge, gaping question remains, perhaps the single biggest question in all of physics today. What is it? This is the frontier, the next case for our cosmic detectives. And it is a case that has stumped the most brilliant minds on the planet for decades. We know what dark matter is not. It's not just faint stars, black holes, or cold gas clouds. Astronomers have looked. The sheer amount of mass required has ruled out all candidates made of ordinary matter. It has to be something new, something completely outside the standard model of particle physics. This is both incredibly frustrating and thrilling. It means there's new physics waiting to be discovered. Scientists have no shortage of theories, no lack of suspects for the identity of the dark matter particle. One of the longest-standing candidates is a class of particles known as WIMPs, which stands for Weakly Interacting Massive Particles. As the name suggests, these would be heavy particles that interact only through the weak nuclear force and gravity. This weakly interacting nature is key. It's why they are so hard to detect. To hunt for WIMPs, physicists have built extraordinary experiments deep underground. These detectors are essentially pristine, ultra-sensitive vats of material, like liquid xenon, cooled to incredibly low temperatures. The hope is that, out of the trillions of dark matter particles passing through the detector every second, one will, by a sheer fluke, collide with an atomic nucleus. This collision would create a tiny flash of light or a minute vibration that hypersensitive instruments could pick up. Experiments like Lux Zeppelin in South Dakota and XENONNT in Italy are currently listening intently for these faint whispers. So far, they have heard only silence. Another leading suspect is a hypothetical particle called the axion. Axions would be incredibly lightweight, much lighter than WIMPs, and would interact even more weakly with normal matter. If axions are the dark matter, they would form a vast, coherent, wave-like field permeating the galaxy. Experiments trying to detect axions use powerful magnetic fields to try and convert a stray axion into a detectable photon, a tiny flash of light. There are even more exotic ideas. Some recent hypotheses suggest that what we believe to be a supermassive black hole at our galaxy's center might actually be an ultra-dense core of dark matter, which could potentially explain the motions of both the innermost and outermost stars. Other theories question gravity itself. though these alternatives struggle to explain all the evidence, like gravitational lensing. While particle physicists hunt in their labs, astronomers continue their investigation in the sky. The Vera Rubin Observatory, aptly named after the field's pioneer, is poised to be a game-changer. Over 10 years, it will survey the entire southern sky repeatedly, creating the deepest, widest map of the universe ever made. Its data will allow scientists to map the dark matter halo with exquisite precision using the weak gravitational lensing of billions of galaxies, providing crucial data to test theories about the nature of the dark matter particle. We are living in a unique moment. We've sketched the outline of a ghost, and now we are building the tools to finally see its face. So, we return to where we began, staring up at that familiar, shimmering band of light in the night sky. But it's no longer the same. We now see it for what it truly is, a beautiful, brilliant, and captivating lie. It is the glowing filament in an invisible bulb. It is the visible peak of a mountain of darkness. The true galaxy, our home, is a colossal, silent, and invisible halo of dark matter. A weirdly shaped, tilted structure stretching nearly 2 million light-years from end to end, with a total mass of over 1 trillion suns. This structure, born in the dawn of time, acted as the cosmic cradle for the stars and gas that would eventually form our sun, our planet, and ourselves. Its gravity holds us together and protects us from being flung into the intergalactic void. We live inside this giant. We are part of it. The discovery of this dark halo is a profound lesson in humility. It reminds us that our senses perceive only a sliver of reality and that the universe is under no obligation to be simple or intuitive. It's far grander, far stranger, and far more mysterious than we ever imagined. We've come on a long journey, from the first puzzling motions of the stars to the grand cosmic architecture of the universe. We've followed the clues, unmasked the giant, and now stand before the final, deepest mystery. What is this dark substance that constitutes the vast majority of our home? The hunt is on, and the answer, when it comes, will mark the next great leap in our cosmic journey. The universe just got a whole lot bigger, and a whole lot darker. And that makes the small, fragile light of our existence all the more precious. What do you think dark matter is? A new particle? A flaw in our understanding of gravity? Let me know your thoughts down in the comments. I'm genuinely curious to hear what you think. And if you want to join me on more journeys to the edge of what we know, to explore the biggest questions in the cosmos, make sure you're subscribed and have those notifications turned on. Part 2: What dark matter actually means. The phrase itself sounds mysterious before we even understand it. Dark matter. It almost feels like the kind of term people would invent for poetry, or for mythology, or for something hidden behind the stars. It sounds dramatic, maybe even a little ominous. And because of that, it is very easy to imagine dark matter as some kind of cosmic fog, or a black fluid floating through space, or a strange invisible smoke surrounding galaxies. But that is not really what scientists mean. And before we go any further into the true scale of the dark matter around our galaxy, it helps to slow down here, for just a little while, and ask a simple question. When astronomers say, dark matter, what are they actually talking about? Because the answer is both more ordinary and more unsettling than it first appears. Dark matter is not called dark because it is evil, or because it is made of darkness in the way night is dark. It is called dark for a quieter reason. It does not give off light. It does not glow. It does not shine. It does not reflect sunlight into our telescopes, and it does not absorb and re-emit radiation in the same easy way that ordinary matter often does. In the most direct sense, it is dark because it does not show itself to us the way stars, planets, dust clouds, or hot gas do. It hides from the instruments that human beings first learned to trust. That alone makes it strange. Most of what we know about the universe began with light. We learned about the moon because we could see it. We learned about planets because they moved against the background of stars. We learned about galaxies because telescopes revealed their glow. So much of astronomy is really the study of light in all its forms. Visible light, infrared light, X-rays, radio waves. Again and again, we point our instruments into the sky and wait for something to arrive. Dark matter does not arrive that way. It leaves no easy glow for us to collect. No bright signature. No soft color. No glittering trail. If the universe were a stage, ordinary matter would be the actors standing under the lights, while dark matter would be the weight of the building itself, holding the whole theater together from the shadows, never stepping forward, never taking a bow. And yet, even though we cannot see it directly, scientists speak of it with remarkable seriousness. Not because they are guessing wildly, and not because the idea is fashionable, but because something invisible appears to be shaping the universe in a very real way. Something unseen seems to be pulling on stars, bending the paths of galaxies, and helping large cosmic structures hold together. So dark matter, in the simplest possible language, is the name we give to whatever this invisible mass is. That is a useful way to think about it, not as a fully understood thing, but as a label for a mystery with very specific behavior. When astronomers say dark matter, they are not claiming that they have already solved everything. They are saying something more careful. They are saying that the universe behaves as though there is more mass present than we can account for with normal, visible matter alone. More gravity than expected. More pull than the shining parts of the cosmos can explain. It is the name for the missing weight. And perhaps that is the most important idea to hold on to. Dark matter is not primarily an idea about appearance. It is an idea about gravity. If you had to forget almost everything else and keep just one sentence in mind, it would be this. Dark matter is something we infer because of the gravitational effects it seems to produce. That word, infer, matters a great deal. In daily life, we do this kind of thing all the time. You do not see the wind itself, but you see leaves moving, curtains lifting, dust drifting across a road. You do not see gravity as a color or a texture, but you see an apple fall, a child swing back toward the ground, the moon circling Earth. So much of reality is known not by direct sight, but by effect. We learn to trust invisible causes because of visible consequences. Dark matter belongs to that category. It is not visible in the way a star is visible, but its fingerprints seem to be everywhere. And that brings us to another very important distinction. Dark matter is not just stuff we cannot see yet. It is not simply ordinary matter hiding in the dark. That possibility was considered very seriously for a long time. Maybe the universe's missing mass was locked up in dim stars, or cold clouds of gas, or dead worlds drifting between galaxies, or black holes too quiet to notice. Those ideas are understandable. If something is missing, the simplest first guess is that it is ordinary and merely hidden. But the deeper astronomers looked, the less that explanation seemed to work. There is not enough faint ordinary matter hiding in the dark to explain what galaxies are doing. Not enough cold gas. Not enough failed stars. Not enough burnt-out embers. The missing mass problem appears too large, too persistent, and too widespread. That is why dark matter became such a serious idea. Not because scientists wanted something exotic, but because familiar answers kept falling short. In that sense, dark matter is a very scientific kind of mystery. It did not begin as fantasy. It began as frustration. The universe was not behaving the way it was supposed to. And so astronomers were forced into a humbler position. They had to admit that either their understanding of gravity was incomplete, or there was more matter in the cosmos than they could see. Maybe both. But certainly something important was missing from the picture. That picture, by the way, is worth pausing on. When most of us imagine the universe, we imagine the visible universe. Stars, nebulae, planets, galaxies. rings of Saturn, the bright core of the Milky Way, the glowing gas in distant clouds. Even when we imagine emptiness, we are imagining the emptiness between visible things. But the modern scientific picture is far stranger than that. Ordinary matter, the matter that makes stars, trees, oceans, people, and everything you have ever touched, may be only a small fraction of the total cosmic inventory. The visible universe is not the whole universe in any practical sense. It may not even be the main part. That is a deeply disorienting thought. It means the universe we know through direct experience may be only the thin, bright surface of a much larger invisible reality. It means that light, for all its beauty, may be telling us only part of the story. And it means that galaxies like our own Milky Way may be structured not mainly by what shines, but by what does not. Now, this does not mean dark matter is magical. It does not mean it can do anything at all. In fact, one of the reasons it is so difficult to study is that it seems oddly quiet. It does not appear to interact strongly with light. It does not clump into stars the way ordinary matter does. It does not build glowing planets or fiery suns. It seems to pass through the luminous universe without joining in the brilliant drama we are used to watching. It is there, and yet not there in the familiar way. Imagine building a city at night. The lights in the windows, the traffic below, the glow of signs and towers, those are like ordinary matter. They are obvious. They announce themselves. They are what you notice first. But beneath all of it, hidden in darkness, is the steel frame, the concrete foundation, the buried supports carrying the weight of everything above. That hidden structure does not flash or sparkle. It is not what most people come to admire. But without it, the city would not stand in the same way. Dark matter seems to be something like that for the cosmos. Not the decoration, not the bright face, the hidden architecture. And once you begin to see it that way, a lot of things start to feel different. The night sky becomes stranger. That beautiful band of stars we call the Milky Way no longer feels like the complete object. It begins to feel more like a luminous clue. A visible core embedded inside something vastly larger. A kind of glowing center inside an invisible domain. What we call our galaxy may be, in some sense, the bright expression of a much greater structure built mostly from something we still do not fully understand. This is why dark matter matters so much. Not only because it is a scientific puzzle, but because it changes the scale of what we think we are living inside. If ordinary matter is the familiar furniture of the cosmos, dark matter may be the house. And still, even with all of that said, it is important to stay grounded. Because one of the easiest mistakes to make with dark matter is to imagine it too dramatically. It is very tempting to give it a personality. To make it feel active, sneaky, almost conscious. But science is quieter than that. Dark matter is mysterious, yes. But mystery does not mean fantasy. It simply means that the evidence points to something real before we fully know what that thing is. That happens in science more often than people think. In fact, some of the most important discoveries begin this way. First, a pattern. Then a mismatch. Then a stubborn anomaly. Then a name for the thing causing the trouble. Only later, sometimes much later, comes the deeper explanation. Dark matter sits in that difficult middle stage. We have the name. We have strong reasons to use it. We have many observations that support the idea that something unseen is adding mass and shaping structure. But we are still living before the final reveal. We are still in the chapter where we know the outline of the invisible giant, but not yet its true identity. And there is something almost beautiful about that. Because it reminds us that science is not a list of final answers. It is a disciplined way of listening when reality refuses to match our expectations. The universe, in this case, seems to be telling us that most of the mass in and around galaxies is not made of the familiar shining stuff. It seems to be telling us that the bright Milky Way in our sky is only part of a much bigger story. And it seems to be telling us that gravity is one of the only languages this hidden matter is willing to speak. So perhaps the simplest honest definition is this. Dark matter is the invisible mass that seems to reveal itself through gravity, even though it does not reveal itself through light. That may not sound poetic at first, but if you sit with it for a while, it becomes extraordinary. It means there may be vast structures around us right now that no human eye could ever naturally see. It means our solar system is moving through an unseen environment. It means that every star in the Milky Way may be tracing its path inside a larger gravitational framework, one we did not evolve to notice. And it means that for all our progress, we are still living in a universe whose main ingredients remain partly hidden from us. That is not a failure of science. It is one of the reasons science stays so alive. Because the cosmos still has the power to humble us. A long time ago, people thought Earth was the center of everything. Then we learned we orbited the sun. Then we learned the sun was one star among many. Then we learned the Milky Way was one galaxy among billions. And now we find ourselves confronting another humbling possibility. Even the galaxy we call home may be mostly defined by something we cannot directly see. Each step removes us a little further from the center. And each step, strangely, makes the universe grander. There is also something deeply human in the way we came to this realization. We did not discover dark matter by seeing farther in the usual sense. We discovered it by noticing that reality was heavier than it looked. That the visible universe was not enough. That the motions of the cosmos were carrying a secret. In that way, dark matter is almost like a whispered correction from the universe itself. You are measuring the right thing, it says. But you are not counting everything. If you enjoy these slow journeys into the hidden structure of reality, you can quietly subscribe and stay for the next one. And if you feel like it, you can leave a comment about where in the world you're listening from tonight. There is something fitting about people across Earth lying beneath the same invisible halo, all wondering about the same unseen universe. Now, there is one last idea we should leave with before this part comes to a close. Dark matter is not just important because it adds missing mass. It is important because it changes the question. Instead of asking only, what can we see out there? Astronomers had to start asking, what unseen thing would make the visible universe behave this way? That is a much more powerful question. It shifts science from simple observation into deeper interpretation. It forces us to read the universe indirectly, the way you might read the presence of an animal by tracks in snow, or the path of a ship by the wake it leaves behind. Dark matter may be invisible, but invisibility is not the same as absence. Sometimes the most important parts of reality are known only by the way they shape everything else. And that is exactly what makes this topic so captivating. Not just that dark matter is hidden, but that the universe seems built to reveal hidden things slowly, piece by piece. Effect before identity. Influence before understanding. First, the strange behavior. Then the clue. Then the long patient effort to name what cannot yet be held. So for now, that is enough. Dark matter is not a black cloud. Not cosmic smoke. Not simply darkness itself. It is the name we give to the unseen mass whose gravity seems to shape galaxies, hold structures together, and quietly dominate far more of the universe than the bright matter we know so well. The stars are the part we notice first, but they may not be the part doing most of the holding. And once that idea settles in, the Milky Way begins to look different, less like a complete object, and more like a lantern hung inside a much larger invisible house. In the next part, we can begin following the first clues more closely. Because once astronomers started to suspect that something unseen was there, the obvious question became impossible to ignore. How did they know? And why did the stars begin to betray the secret? Part 3, the first clue: something invisible was there. At first, nothing looked wrong. That may be the most unsettling part of the whole story. The stars still shone. The Milky Way still stretched across the night in its familiar pale band. Telescopes still revealed spiral galaxies turning slowly in the darkness, elegant and graceful, like glowing pinwheels suspended in black water. If you had looked at the universe with your eyes alone, you would have had no reason to suspect that anything was missing. It all seemed complete. Beautiful, yes. Vast, certainly. But complete. And yet, the first real clue that something invisible was there did not come from a strange object suddenly appearing in the sky. It did not come from some dramatic flash, or a cosmic explosion, or a mysterious signal from deep space. It came from something much quieter than that. It came from motion. From the simple question of how things move when gravity is doing the pulling. This is one of those moments in science that feels almost gentle at first. So gentle, in fact, that it can be easy to miss how profound it really is. Because the question sounds so ordinary. If a galaxy is full of stars, and those stars are all orbiting the center of the galaxy, then how fast should they move? That is it. That is where the trouble began. And like so many important questions, the answer seemed obvious before anyone looked carefully. To understand why, it helps to start close to home, in the quiet familiarity of our own solar system. Here, we live inside a gravitational system that behaves in a way that makes sense to us. The Sun sits at the center with almost all the mass. The planets orbit around it. The closer a planet is to the Sun, the faster it tends to move. Mercury races around the Sun much more quickly than Earth. Earth moves faster than Jupiter. Jupiter moves faster than Neptune. The farther out you go, the weaker the pull from the concentrated central mass seems to become, and the slower the orbital motion gets. This pattern feels natural because it matches our intuition. If most of the weight is piled up near the middle, then the outer regions should not need to move as fast to stay in orbit. If they did move too fast, they would no longer remain bound in the same way. They would drift away. Astronomers expected galaxies to follow a similar basic logic. After all, if you look at a spiral galaxy, most of the visible light is concentrated toward its center and inner regions. There is a bright bulge, then spiral arms, then a fading edge. The visible matter seems densest near the middle, thinner farther out. So the expectation was simple. Stars closer to the center should move quickly. Stars farther away, especially near the outer parts of the visible galaxy, should move more slowly. That was the tidy expectation. The sort of expectation that makes everyone feel comfortable. And for a while, comfort lasted because measuring the true motions of stars across an entire galaxy is not easy. Galaxies are far away. Their stars blur together. Their structures are beautiful, but difficult to translate into exact motion. For a long time, astronomers could see galaxies, classify them, photograph them, admire them, even begin to understand their forms. But measuring their detailed internal motion with precision was a harder task. It required better instruments, better methods, more patience. And eventually, that patience began to pay off. As telescopes improved and spectrographs became more powerful, astronomers found ways to measure how fast matter in galaxies was moving. They did this by studying light very carefully, because light carries motion hidden inside it. When something in space is moving toward us, the light it emits shifts slightly toward the blue end of the spectrum. When it moves away, the light shifts slightly toward the red. This is known as the Doppler effect, and once you understand it, the universe becomes full of motion that was always there, waiting quietly inside light. It is a lovely thing, really. Even when stars are too distant to touch, even when galaxies are impossibly far away, the light still brings news of movement. Light becomes a messenger. And what that messenger began to report was deeply strange. When astronomers measured how fast material was orbiting in spiral galaxies, especially in their outer regions, the numbers did not fall the way they were supposed to. The speeds remained stubbornly high. Far from the bright center, where the visible matter had thinned out and the gravitational pull should have weakened, stars and gas were still moving at speeds that seemed too large. Too large for what the eye could justify. Too large for the visible matter alone. This was not a small mismatch, not a tiny correction that could be brushed aside as a measurement error or an awkward detail. It was a serious discrepancy. The outer parts of galaxies were behaving as if there were much more mass present than anyone could actually see. Imagine walking into a dimly lit room and seeing a chandelier sway gently from side to side. If it moved only a little, you might think there was a mild breeze. But if it swung hard, as though a door had just slammed, and yet every window was closed and the air was still, you would know something was missing from the story. The visible scene would not be enough to explain the motion. That was the feeling astronomers began to have. The motion was too strong for the visible cause. And once that kind of mismatch enters science, it becomes very hard to ignore. Because motion, unlike appearances, is difficult to flatter. A galaxy may look serene, but its stars still have to obey gravity. A beautiful spiral shape does not excuse impossible orbits. The universe can be mysterious, but it is not careless. If something is moving in a certain way, there must be some reason. This is where the story becomes quietly thrilling. Because in those moments, astronomy stops being only the study of distant beauty and becomes a kind of detective work. The stars are no longer just stars. They are witnesses. Their motion becomes testimony. And their testimony said the same thing over and over again. There is more here than you can see. Now, one of the most important figures in this chapter of the story was Vera Rubin, whose work helped turn a troubling suspicion into one of the strongest arguments in all of modern cosmology. She was not the first person ever to wonder if galaxies contained unseen mass. Earlier astronomers had noticed hints of the problem in galaxy clusters. But Rubin's careful work on the rotation of spiral galaxies helped make the mystery impossible to dismiss. Night after night, measurement after measurement, the same pattern appeared. The rotation curves were too flat. That phrase may sound technical at first, but the idea behind it is actually simple. A rotation curve is just a way of plotting how fast stars or gas move at different distances from a galaxy's center. If galaxies behaved the way people originally expected, the curve would rise near the middle, then fall farther out. But that is not what the data showed. Instead, the speed rose and then stayed high, much farther out than it should have. Flat. Steady. Wrong, according to the visible matter alone. That flatness became one of the great clues in the story of dark matter. And it is worth slowing down here, because this is the moment when the invisible begins to announce itself without ever becoming visible. No dark cloud appears. No hidden object steps into the light. Instead, the galaxy's outer regions move as though they are being held by extra gravity. The stars continue their wide silent orbits as though they are embedded in a much larger gravitational field than the shining galaxy seems to provide. In other words, the visible galaxy looked too light for the motion it contained. If that sounds abstract, it may help to picture a merry-go-round. If the center is sturdy and the outer edge is moving only gently, everything feels normal. But if the outer edge is whipping around very fast, then you know the system must be supported by more force, more structure, more strength than it appears at first glance. Otherwise it would fly apart. Galaxies were not flying apart. That alone was one of the biggest clues. The outer stars in spiral galaxies were moving so quickly that, if only the visible matter were present, many of them should not have remained bound in the way they did. And yet there they were, still orbiting, still held, still tracing vast patient circles through space. Something was keeping the structure together. Something invisible. This is a beautiful example of how science sometimes works best not when reality answers our questions, but when it resists our assumptions. The universe did not hand astronomers a neat labeled box called dark matter. It simply refused to behave according to the visible script. And in that refusal, it revealed that the script was incomplete. That is often how hidden truths emerge. Not through direct revelation, but through stubborn inconsistency. The galaxies were not saying, "Here is dark matter." They were saying, "Your current picture is too small." And that difference matters. Because it means dark matter was not invented out of nowhere. It was not added to make the equations look fancy. It was proposed because the ordinary picture no longer held together. It was a response to evidence, to motion, to gravity, to repeated patterns across many galaxies. The idea grew not from imagination alone, but from pressure exerted by the data itself. There is something almost philosophical about that. Human beings are often tempted to trust what is visible most of all. We see the bright center of a galaxy and assume that is where the story mostly is. We see the stars and think they are the galaxy's main substance. But the motions of those same stars suggest a humbling correction. The bright parts may not be the main part. The visible may not be the dominant. What shines may be only a trace. That is not just a scientific idea. It is a shift in perspective. It asks us to accept that the universe may be structured most deeply by things that do not announce themselves to the eye. And perhaps that is why the story of dark matter feels so powerful. It is not just about an invisible substance. It is about the limits of appearances. Now, of course, scientists did not jump immediately to a final conclusion. That is not how careful work happens. Other possibilities had to be considered. Could the measurements be wrong? Could there be hidden clouds of gas? Could there be many faint stars too dim to see easily? Could gravity behave differently on large scales? These were all fair questions. And over time, they were tested. But the basic problem did not go away. The mismatch between visible matter and observed motion kept showing up, not just in one galaxy, but in many. Again and again, the outer regions moved as though they belonged to something larger, heavier, and more extended than the bright stellar disk. This is where the idea of the dark halo began to take shape. If the extra mass was real, and if it was not concentrated only in the bright center, then perhaps galaxies were embedded inside vast halos of unseen matter. Not a small hidden object tucked inside them, but a huge diffuse structure surrounding them. A kind of invisible sphere, or at least an enormous enveloping region, extending far beyond the visible stars. That idea changed everything. Because once you imagine a galaxy this way, the familiar glowing disk is no longer the whole system. It is more like the visible core of something much larger. The stars we see become the lit interior of an invisible gravitational domain. And suddenly the problem of dark matter becomes a problem of scale. Not just what is missing, but how far it goes. Not just what extra mass is present, but what kind of hidden structure it forms. That question, the question of extent, is the one that will eventually lead us toward the astonishing scale of the Milky Way's dark matter halo. But before we get there, it is worth sitting a little longer with this first clue, because it was more than a technical puzzle. It was a turning point in how human beings understand galaxies themselves. Before this, it was easy to think of a galaxy as mostly what you could photograph. A bright island of stars. A graceful arrangement of light. But after these measurements, that idea began to feel incomplete. A galaxy could no longer be defined only by its visible appearance. Its invisible gravitational body had to be taken seriously too. The galaxy was becoming bigger than its glow, heavier than its light, stranger than its shape. And I think there is something wonderfully calming in that realization, even though it began as a scientific problem. Because it reminds us that reality is under no obligation to fit neatly inside the first picture we form of it. Sometimes understanding deepens when certainty loosens. Sometimes the universe grows more beautiful exactly when it becomes less familiar. The Milky Way, seen from Earth, is already one of the most moving sights in nature. A pale river of stars crossing the dark. But once you understand that the visible band may be only the bright middle of a much larger invisible structure, the beauty becomes deeper. The sky does not become less enchanting. It becomes more layered, more honest, more immense. If you are enjoying this slow unfolding of the cosmos, you can gently leave a like, or subscribe if you want more quiet journeys like this one. And if you feel like sharing, I always enjoy hearing where people are listening from. It is a comforting thought that so many of us, in different rooms and cities and time zones, are all resting beneath the same unseen galactic halo. By now, the first clue is clear. Dark matter did not enter astronomy because someone wanted the universe to sound mysterious. It entered because galaxies were moving in a way that visible matter could not explain. The stars, especially in the outer parts, were going too fast for the gravity we could account for. The mismatch was too consistent to ignore. The visible Milky Way, and galaxies like it, seemed to be only part of a larger gravitational reality. That was the beginning. Not the full case. Not the final proof. But the beginning. The moment when motion betrayed the secret. The moment when astronomers first began to suspect that galaxies were wearing a visible mask over an invisible body. And once that suspicion took hold, the next step was inevitable. If stars were offering the first clue, then scientists would have to look even more carefully at what gravity was doing elsewhere. Not just in galactic rotation, but across larger systems, deeper distances, and stranger cosmic arrangements. Because if something unseen was really there, it would not leave only one fingerprint. It would leave many. And in the next part, those fingerprints begin to appear everywhere. Part 4: Why the Milky Way should have fallen apart. If the previous clue was a whisper, this next one feels more like a quiet alarm. Because once astronomers realized that stars in galaxies were moving in a very unexpected way, a more serious question rose naturally behind it. It was no longer just a matter of curious numbers on a graph. It became a question about survival. How is the galaxy still here? That is really what this part of the story comes down to. Not just why stars move the way they do, but why the whole structure of the Milky Way has not slowly unraveled over cosmic time. Why its outer stars have not drifted off into the black. Why its graceful shape has not dissolved into something looser, thinner, more chaotic. Why a galaxy that appears so delicately arranged has remained held together at all. Because once you begin looking carefully at the motion of stars, especially far from the galactic center, the Milky Way starts to seem less stable than it looks. And yet, there it is. Still turning. Still coherent. Still quietly carrying us around the galaxy at enormous speed. There is something almost soothing about that contrast. On the one hand, the universe appears violent in scale. Everything is moving. Everything is under gravity's influence. Nothing truly rests. And yet the structures that emerge from all that motion can seem calm and enduring. A spiral galaxy from a distance looks like a still image. Serene. Balanced. Almost decorative. But the truth is much less still than that. The Milky Way is in motion everywhere. The sun is moving around the galactic center. The stars in the spiral arms are moving. Gas clouds are moving. Globular clusters are moving. Small satellite galaxies orbit and interact with it. Even our local neighborhood is not sitting inside some quiet cosmic painting. It is part of an immense gravitational system, and that system is only stable if enough mass is present to hold it together. That is the key. A galaxy is not held together by beauty. It is held together by gravity. And gravity depends on mass. The more mass a system has, the stronger its gravitational pull can be. That is true here on Earth, and it is true on the scale of stars and galaxies. If you want a star to remain in orbit around the center of the galaxy, there must be enough gravity pulling inward to balance the tendency of that star to continue forward through space. What we call orbit is really that balance. Inward pull against onward motion. Neither a fall straight inward, nor an escape straight outward. It is a delicate arrangement, but it is not mysterious in itself. What becomes mysterious is when the visible mass does not seem sufficient to produce the gravity required. And that is exactly the problem the Milky Way presents. Now, we should be a little careful here. Galaxies are not as simple as the solar system, and it would be misleading to imagine every star behaving like a planet around a sun. The mass of a galaxy is more spread out. The central bulge contains many stars, yes, and the inner regions are dense, but a galaxy is not a single compact object. It is a vast distribution of matter. So the details are more complex. Still, the central idea remains. If most of the galaxy's visible matter is concentrated toward the middle and inner disk, then stars much farther out should, in general, feel less gravitational pull from that visible matter than stars closer in. And if that inward pull weakens with distance, then outer stars should not need to move so fast to remain gravitationally bound. In fact, if they do move too fast, they should escape. This is where the problem becomes almost impossible to ignore. Because many stars in the outer parts of galaxies, including the Milky Way, appear to move at speeds that are too high to be explained by visible matter alone. They are not moving just a little too fast. They are moving fast enough that, if the galaxy contained only the stars, gas, and dust we can account for directly, the outer structure should not remain intact in the way it does. The galaxy should be looser, less tightly held, more prone to flying apart over long stretches of time. And yet it has not. To feel the strangeness of that more clearly, it helps to picture something familiar. Imagine swinging a stone tied to a string in a wide circle. As the stone moves, the string provides the inward pull that keeps the path curved. If you swing it faster and faster, the tension in the string has to increase. If the inward pull is too weak for the speed involved, the stone does not stay in the circle. It breaks free. The galaxy has no literal string, of course. Gravity is doing that work. But the principle is very similar. The faster a star moves in its orbit, the stronger the inward gravitational pull must be to keep it from escaping into intergalactic space. That is why the outer stars became such a problem. Their speed implied the need for more inward pull. More pull implied more mass. And more mass implied something unseen. Without that extra hidden mass, the visible Milky Way should not behave the way it does. Its outskirts should be far less stable. Stars in the outer regions should be far more vulnerable to drifting away. Over billions of years, the galaxy should have shed much more of itself into the surrounding dark. But the Milky Way is old, very old. It has existed for billions upon billions of years. Long enough for unstable structures to reveal themselves. Long enough for weakly bound outskirts to loosen. Long enough for a galaxy built only from the visible matter we know to show more obvious signs of coming apart. Instead, what we see is a galaxy that has endured. Not unchanged, of course. Galaxies evolve. They merge, feed on smaller companions, stir their gas, form new stars, and slowly reshape themselves. The Milky Way has had a long dynamic history. But through all of that, it has remained a coherent galaxy. A functioning gravitational system. A place where stars continue to orbit rather than simply disperse into the void. Something has been holding it together. And once again, the visible mass seems insufficient. This is one of the most important emotional turning points in the dark matter story. Because it takes the idea out of the realm of abstract missing numbers and places it into a more intuitive one. The galaxy we live in appears to need help remaining a galaxy at all. That invisible help seems to be real. It is not an extra detail painted onto the edges of astronomy. It may be one of the main reasons large galaxies can exist in the stable forms we recognize. In this sense, dark matter begins to look less like a strange add-on and more like a hidden structural necessity. Without it, the Milky Way may never have become what it is. Or, if it did form, it may never have remained so grand, so wide, so enduring. Now there is a very quiet and beautiful irony here. When we look at the Milky Way from Earth, the visible part feels ancient and trustworthy. A river of stars. A celestial constant. Something our ancestors saw and marveled at long before the first telescope. It gives the impression of a complete thing. Something self-contained. Something resting in its own visible majesty. But in truth, The galaxy may be more like a lantern whose visible glow depends on an invisible frame around it. What we notice first is not necessarily what matters most. That is the lesson dark matter keeps teaching us. A galaxy may shine because of stars, but it may survive because of something else. And that survival matters more than it might first seem. Because if galaxies were not held together effectively, then the environments needed for long-lived stellar systems, planetary systems, and eventually life would be much less common or much less stable. The calm continuity we enjoy here, on a planet orbiting a middle-aged star in a relatively quiet spiral arm, depends on large structures having remained gravitationally coherent over immense spans of time. That coherence is not trivial. It is one of the hidden conditions behind our existence. So when scientists say the Milky Way appears to sit inside a vast halo of unseen matter, this is not just a statement about scale. It is also a statement about support. The dark halo is not merely something around the galaxy. It may be the main gravitational body that allows the visible galaxy to be what it is. It is very easy to miss how radical that idea is. Because we are used to thinking of the stars as the main event. The stars are what we photograph. The stars are what fill our myths. The stars are what define constellations, stir emotion, and make the sky memorable. In our imagination, the galaxy belongs to the stars. But the growing scientific picture suggests something more humbling. The stars may be guests. Or perhaps decorations. Beautiful, yes. Precious, certainly. But not the full foundation. The true mass of the galaxy may reside mostly in something that does not glow at all. And if that is true, then the Milky Way did not merely avoid falling apart by chance. It avoided falling apart because it lives inside a much larger gravitational structure than the one our eyes can see. This helps explain why the outer regions of galaxies are such powerful evidence. The farther you go from the bright center, the more the mismatch matters. If those distant stars were slow, the visible picture might be mostly acceptable. But because they remain fast, the need for extra mass becomes much more difficult to escape. The outer galaxy behaves as though it is still deep inside an extended gravitational field. That is the quiet revelation. The visible edge is not the real edge. The glow fades before the gravity does. And once you realize that, the shape of the problem changes entirely. You stop imagining the galaxy as a bright disk with maybe a few hidden details. Instead, you begin imagining a bright disk embedded in something much larger, much heavier, and much more diffuse. Something extending far beyond the stars we can easily see. That hidden extension is what later came to be understood as the dark matter halo. But before the halo became a widely accepted picture, astronomers had to sit with the discomfort of the basic fact itself. The Milky Way, if composed only of visible matter, appeared too fragile for its own motion, too light for its speed, too delicate for its endurance. That is a serious thing for science to discover, because science becomes strongest when appearance and behavior no longer match. A galaxy may look one way, but if it moves another way, then behavior must win. Nature does not grade itself on visual impressions. It follows physical law whether the result feels intuitive to us or not. And the law here was clear. Fast-moving outer stars require enough gravitational pull to keep them bound. If visible matter cannot supply that pull, something else must. There is another way to feel this intuitively. Imagine a vast carousel in darkness, with lights only near the center and middle. You are allowed to see the glowing horses and the bright inner ring, but the outer structure is hidden in blackness. Then someone tells you how fast the outer edge is moving. Not slowly, but surprisingly fast. Fast enough that the visible supports near the middle should not be enough to hold the full structure together. At that point, you would not conclude that the motion is magical. You would conclude that there must be more support hidden in the dark than you can presently see. That is what astronomers were forced to conclude about galaxies. Not magic. Hidden support. Hidden mass. This is also why dark matter came to be understood not mainly as a collection of invisible objects sprinkled through the disk, but as a large, extended halo. A halo can provide gravitational influence well beyond the bright stellar regions. It can hold the outskirts in its grip. It can explain why stars far from the center are still moving as though they belong to a much heavier system than the visible galaxy suggests. And if that halo is real, then the galaxy has been living inside a hidden architecture all along. A hidden architecture that not only affects motion, but preserves structure. There is something almost comforting in that thought. The Milky Way is not barely surviving on the strength of its visible stars alone. It is resting inside a deeper gravitational shelter. The night sky may look fragile, but underneath that beauty there is immense unseen weight. A great silent framework, carrying the galaxy through time. If this kind of calm exploration helps you unwind, you can quietly subscribe and return for more of these journeys. And if you feel like leaving a comment, I always enjoy hearing what part of the world you're listening from. It is a gentle thought, really, that people in so many different places are all drifting off beneath the same galaxy, held by the same invisible halo. Now, there is one more layer to this question of falling apart, and it is perhaps the most profound one. The Milky Way is not only a structure that remains bound today. It is also a structure that had to form in the first place. And to form a large spiral galaxy, ordinary matter must gather, cool, settle, and remain gravitationally organized over immense time. If the underlying gravitational environment were too weak, too shallow, or too easily disturbed, the visible galaxy would struggle not only to stay together, but to emerge in such a stable form at all. So the dark matter problem is not merely about maintenance. It may be about possibility. The invisible mass around the galaxy may not only explain why the Milky Way has not fallen apart. It may explain why a galaxy like ours could ever become our home. That is a bigger and quieter thought than it first seems. It means that when you look up into the sky and imagine the Milky Way, you are not just looking at a beautiful arrangement of stars. You are looking at the visible outcome of a much deeper gravitational history. The galaxy's glowing disk may be the luminous expression of an invisible skeleton that came first, or at least that shaped everything that followed. The stars tell the story we can see. The dark halo may tell the story that made the stars possible. And that is why this part matters so much. Because it is the moment the mystery deepens from simple anomaly into existential necessity. The galaxy should have been more fragile than it is. The visible mass should not have been enough. The outer stars should have had less reason to remain. The whole great wheel of the Milky Way should have been looser, more vulnerable, more prone to losing itself into the darkness. But it did not. It held. It lasted. It remained. And in that endurance, the invisible left one of its clearest signatures. So by the end of this part, the question is no longer whether something unseen might be present. The question is becoming harder, larger, and more fascinating. If this hidden mass is really what holds the Milky Way together, then where exactly is it? How is it arranged? What shape does it take around the galaxy? Because the answer, once it begins to emerge, will reveal that the bright Milky Way we know is not the whole structure at all. It is only the glowing center of something vastly larger. Part 5: The Dark Halo Around the Milky Way. By this point in the story, the old picture of the galaxy has started to feel too small. Not visually small, of course. The Milky Way is still immense beyond any ordinary human scale. It still holds hundreds of billions of stars. Its spiral disk still stretches across a distance so large that even light, moving faster than anything else in the universe, would need around 100,000 years to cross from one side of the visible disk to the other. That is not small in any meaningful sense. And yet, once you begin to understand the problem of motion, the problem of missing mass, and the strange fact that the galaxy appears too stable for its visible matter alone, the familiar image of the Milky Way starts to feel more like a partial truth than a full one. It is not that the galaxy we see is false. It is that it may be only the bright center of something much greater. And that greater thing is what astronomers came to call the dark halo. There is something almost poetic about that phrase, halo. It sounds soft, gentle, almost sacred. It sounds like light, when in fact it describes something that does not shine at all. But the word still works, perhaps because it captures the sense of an enveloping presence, something surrounding the visible body of the galaxy, extending beyond it, shaping it, and quietly defining its true extent. The dark halo is not a ring around the Milky Way in the way Saturn has rings. It is not a shell you could draw with a clean white line. It is not a crisp boundary, and it is certainly not some kind of smoky black cloud wrapped neatly around the stars. It is better imagined as a vast, diffuse region of invisible mass, surrounding the bright stellar disk and stretching far beyond the parts of the galaxy that glow. That is the first thing worth settling into. The Milky Way, as we see it, is not likely sitting alone in empty space. It is likely embedded inside a much larger gravitational structure. And once that idea begins to settle in, the night sky feels different. When most people imagine our galaxy, they picture the bright river of stars visible under very dark skies, or perhaps a spiral galaxy seen in photographs, with glowing arms and a bright central bulge. Those images are beautiful, and they are not wrong. But they are incomplete in the same way a lit window is incomplete if you are trying to understand the size of the house behind it. The visible galaxy is the lit window. The dark halo is the house. Or perhaps, more accurately, the foundation, the walls, and the hidden weight-bearing frame that determines the true size of the structure, even though the eye is drawn only to the illuminated parts. This invisible surrounding mass is not just some optional extra detail added by modern astronomy. It became necessary because the older visible-only models simply did not explain what galaxies were doing. The outer stars kept moving too quickly. The structure remained more tightly held together than visible matter alone could account for. The gravity seemed to continue long after the visible light had begun to thin away. So astronomers gradually came to a larger view. If the stars we can see do not contain most of the galaxy's mass, then perhaps the visible disk lives inside a much broader distribution of unseen matter. Not tucked inside the disk, not hiding only in the bright center, but extending well beyond the luminous boundaries that human eyes first learned to trust. That shift is one of the great quiet revolutions in modern astronomy. Because it changes the very meaning of a galaxy. A galaxy is no longer just the stars, gas, and dust we can photograph. A galaxy becomes, in a much deeper sense, a gravitational system whose visible parts may only represent a small inner portion of its true structure. The bright Milky Way is what ordinary matter does inside a much larger dark environment. And that environment, though invisible, is not abstract. It has consequences. It holds. It shapes. It shelters. It determines how stars orbit, how satellite galaxies move, how matter accumulates, and possibly how the galaxy formed in the first place. It is the hidden body of the galaxy. This is a useful moment to slow the imagination down, because the mind naturally wants a picture. If someone says dark halo, the mind asks at once, what does it look like? But that question is a little misleading. Since dark matter does not shine or reflect light in the usual way, the halo does not offer us an image the way a nebula or star cluster does. We do not have a direct photograph of it in the ordinary sense. We infer its presence through gravity, through motion, through the way visible objects behave inside it. So if you want a picture, it has to be a conceptual one. Try this. Imagine standing in a huge dark valley at night. Near the center of the valley there is a city, glowing with warm lights. From a distance, the city seems like the whole event. It is what catches the eye. It is what announces itself. But the city is not floating in emptiness. It sits in a valley whose shape controls the roads, the rivers, the movement of air, the way things gather and settle. Even in darkness, the valley is there. The city makes more sense once you understand the hidden landscape beneath and around it. That is something like the relationship between the Milky Way's visible stars and its dark halo. The stars are the city lights. The halo is the hidden landscape. Only in this case the landscape is not made of rock and soil. It is made of invisible mass, spread across a region so vast that the bright galaxy we know may occupy only a relatively small central zone inside it. There is another reason the idea of the halo matters so much. It explains why the outer galaxy does not simply mark the end of the Milky Way's real influence. To a beginner, it is natural to assume that where the stars fade, the galaxy ends. That feels intuitive. Bright matter seems like the obvious definition of what is there. But the halo teaches a more subtle lesson. Light fades before gravity does. The visible edge is not the true edge. That sentence is worth remembering. Light fades before gravity does. That is one of the reasons galaxies are more mysterious than they first appear. Their visible shapes are not necessarily their full physical reality. A galaxy can continue gravitationally long after it stops being obvious to the eye. In fact, in the case of the Milky Way, what we call the visible galaxy may be only the small bright center of a much larger structure whose dominant mass is invisible. This is where the word halo becomes especially useful. It suggests an extended surrounding presence, something not limited to the glowing disk itself. It also hints, in a gentle way, at the fact that galaxies may be more spherical in their dark component than their bright parts are. The Milky Way's stellar disk is flattened, like a spinning cosmic pancake. But the dark matter surrounding it is thought to extend in a much broader three-dimensional region around that disk. Not a neat perfect sphere, perhaps. Real cosmic structures are not usually that tidy. But certainly something far more extended and enveloping than the visible disk alone. And this helps explain one of the strangest aspects of the whole story. We live deep inside this halo already. Not near its outer limit. Not perched at some obvious boundary, but comfortably inside it, moving through it, carried by it, held by it, every moment of our existence. The Earth, the Sun, the planets, every human city, every ocean, every mountain, every sleeping animal, every drifting cloud, all of it exists inside this invisible galactic structure. We are not looking at it from outside. We are immersed in it. That is such a strange and calming thought. We often speak of looking up into space as though space begins somewhere above us, as though the galaxy is something distant. And in one sense, yes, the stars are distant. The galactic center is unimaginably far away. But in another sense, the Milky Way is not elsewhere. It is our environment. And if the dark halo is the galaxy's deeper structure, then that invisible structure is not merely surrounding the stars in some abstract scientific model. It is surrounding us. Billions of dark matter particles, if particles they are, would be passing through the Earth and through our bodies every second, and we would not notice at all. The halo does not knock at the door. It does not disturb the air. It does not darken the room. It does not hum or glitter or cast a shadow. It is silent. It simply exerts its influence through gravity on the largest scales, shaping the galactic environment in which everything familiar unfolds. There is a wonderful humility in that. To live inside something so large and so important, yet so invisible to our senses. To be held by a structure we did not know existed for most of human history. To realize that while ancient people saw the Milky Way and told stories about its shining band, even that majestic view was only the visible hint of a much deeper cosmic reality. It reminds us that the universe is not arranged according to what is easiest for human beings to notice. Reality does not simplify itself for our convenience. It leaves clues. And when we follow those clues long enough, the cosmos grows stranger, but also richer. Now, when astronomers talk about the dark halo, They are not merely speaking in vague philosophical terms. The halo is a practical scientific idea. It helps explain why stars in the outer disk keep moving as they do. It helps explain the motions of globular clusters, those ancient compact swarms of stars orbiting the galaxy at large distances. It helps explain the behavior of dwarf satellite galaxies, the smaller galaxies that orbit the Milky Way like companions drawn into its much larger gravitational realm. These objects act like test particles in a vast gravitational field. By studying their motions, astronomers can begin estimating how much unseen mass must be present, and how far it extends. This is one of the beautiful things about astronomy. Even when the thing itself cannot be seen directly, the visible universe becomes a kind of instrument for detecting it. The stars become tracers. The satellite galaxies become markers. The motions become measurements. And slowly, through patience and inference, an invisible structure emerges from the behavior of visible things. That is how the halo came into focus, not as an image in the ordinary sense, but as a gravitational truth. There is something deeply satisfying about that. It means the halo is not just a guess floating free of evidence. It is the result of many lines of investigation converging toward the same larger picture. Rotation curves suggested extra mass. The stability of galaxies suggested extra support. The motions of distant objects suggested the galaxy's influence extended farther than the light. And over time, all of these clues began telling one consistent story. The Milky Way lives inside a vast, dark halo. And if that story is true, then the visible disk is only one chapter of the galaxy, not the whole book. This also changes the emotional scale of the Milky Way. Most people already think of the galaxy as incomprehensibly large. But the halo adds a second layer of immensity. It tells us that even the huge visible galaxy we are taught about in books may itself be only the inner luminous region of something much larger. The structure that truly defines the Milky Way's mass and extent may not be the bright disk at all. It may be the dark halo surrounding it. That is a disorienting thought at first, because it weakens our trust in the visible. But then it becomes strangely peaceful. It expands the imagination. It turns the galaxy from a shining object into an invisible environment with a shining interior. It makes the Milky Way feel less like a picture hanging in space and more like a vast cosmic habitat. You begin to understand that when you look up at the stars, you are not just seeing ornaments scattered in emptiness. You are looking into the luminous center of an enormous hidden structure that has shaped their motion, gathered their matter, and held the galaxy together for billions of years. The halo is not outside the story. It is the story underneath the story. And there is one more subtle thing the halo teaches us. It teaches us that the universe does not separate appearance from structure in the way we instinctively do. Human beings are visual creatures. We privilege what glows, what contrasts, what catches the eye. But gravity does not care what is visible. Gravity responds to mass, whether that mass shines or not. So the true structure of the galaxy is written not only in light, but in movement. Not only in brightness, but in what keeps orbiting and what stays bound. This may be why dark matter feels so philosophically powerful. It asks us to imagine that the deepest organizing principles of the cosmos are not necessarily visible at all. The things we notice first may be secondary. The things we never evolved to sense may be the actual foundation. That does not make the visible world less beautiful. If anything, it makes it more precious. The stars become even more astonishing when you realize they are the small bright part of a much larger hidden architecture. Their glow feels less like the whole universe and more like a rare kind of surfacing, a visible bloom inside something predominantly unseen. If you are enjoying this calm descent into the hidden structure of the Milky Way, you can gently like the video, or subscribe if you want more long-form science made for rest. And if you feel like leaving a comment, I always love hearing where people are listening from. It is a lovely thing to imagine people in different countries, different seasons, different stages of the night, all drifting towards sleep under the same invisible galactic halo. By now, the dark halo should feel less like a strange technical phrase and more like a necessary new way of imagining our home galaxy. The Milky Way is not simply a glowing disk. It is a visible disk embedded inside a much larger, mostly unseen gravitational domain. The stars form the lighted center. The dark halo forms the hidden mass around them, and together they create the real galaxy, far bigger and stranger than the eye alone would ever suggest. But there is still a challenge here, because phrases like bigger and much larger can only carry us so far before they become vague. The human mind needs contrast. It needs a before and an after. It needs to feel the scale difference between the galaxy we see and the halo that surrounds it. And that means before we can truly grasp how far the dark halo reaches, we should pause and anchor ourselves once more in the size of the visible Milky Way itself. Because only then will the real scale of the hidden structure begin to land. Part 6. How big the visible Milky Way is first. Before we can truly feel the size of the dark halo, we need to do something very simple. We need to slow down, turn back toward the galaxy we already think we know, and let its visible size settle properly in the mind. Because the danger with cosmic scale is that the numbers begin to lose their weight. 100,000 light years, 27,000 light years, hundreds of billions of stars. These are extraordinary quantities, but after a while they can start to float past the ear like decoration. The human brain hears them, acknowledges them, and then quietly gives up trying to feel them. So before we go any farther into the invisible structure around the Milky Way, we should pause here and build a more grounded sense of the visible galaxy first. Not the dark halo yet. Not the hidden mass. Just the Milky Way as it appears in stars, gas, dust, and light. Because only once that picture is calm and steady can the larger reveal truly land. Now, when people say the Milky Way is about 100,000 light years across, what they usually mean is the main visible stellar disk, the broad flattened region where most of the galaxy's stars, gas, and spiral structure are found. Some estimates stretch a little higher, perhaps 120,000 light years depending on exactly how the edge is defined, because galaxies do not end with a clean line. They fade. Their brightness thins out gradually. Their outskirts become softer, harder to define, more uncertain. But as a comfortable working picture, 100,000 light years is a good place to begin. That alone is already an overwhelming size. A light year, after all, is not a unit of time. It is a unit of distance. It is the distance light travels in 1 year, moving at about 300,000 kilometers per second, or around 186,000 miles per second. Light is so fast that it can circle Earth many times in a single second. It can go from the Moon to Earth in just over a second. It can travel from the Sun to Earth in about 8 minutes. And even with that speed, even with that staggering pace, crossing the visible Milky Way would still take about 100,000 years. That is the first scale we need to breathe into. If a beam of light started from one bright side of the visible galaxy and moved straight across to the opposite side, it would still be traveling when every human civilization you have ever heard of had long since vanished into history. It would still be crossing while languages changed, continents shifted slightly, coastlines altered, mountains weathered, and generations beyond counting were born and gone. 100,000 years is already far longer than recorded human history. And that is only the visible disk. It is useful, perhaps, to imagine it another way. If the Milky Way's visible disk were shrunk to the size of a large dinner plate, then our entire solar system would barely register as a tiny speck. In some comparisons, it becomes smaller than a grain of dust. That means all the planets, all the moons, all the comets, all the asteroids, the Sun itself, and the long orbit of Pluto would be reduced to something almost too small to notice against the galaxy's broader structure. And we, living on Earth, often feel as though we inhabit something large. The Earth seems large to us because we are small. The solar system seems enormous because our daily lives unfold within a single planet's atmosphere. But cosmic scale quietly corrects those instincts. The solar system is not a major district of the Milky Way. It is not even a neighborhood in the sense we emotionally imagine. It is more like a single dust mote drifting in one small suburban lane of a galaxy so wide that even light takes ages to cross it. And where are we inside this visible disk? Not in the center. That is an important fact, and one worth lingering on for a moment, because human beings often imagine themselves nearer the middle of things than they really are. But in the Milky Way, we are not at the center of the galaxy. We are not even close to it in the everyday sense. Our solar system lies roughly 26 to 27,000 light-years from the galactic center, give or take depending on the estimate used. We sit in a relatively modest region of the galaxy, inside a smaller spiral feature called the Orion Spur, between larger spiral arms. We are not in the crowded brilliance of the central bulge. We are not in the outermost fringe either. We are somewhere in the broad middle distance, orbiting the center as one small part of the great galactic wheel. That orbit itself is another beautiful reminder of scale. The Sun, carrying Earth and the rest of the solar system with it, travels around the center of the Milky Way at an enormous speed. We are moving through the galaxy much faster than the body ever senses. Yet because the distances involved are so vast, it still takes around 220 to 250 million years for the Sun to complete one orbit around the galaxy. One galactic year, if you like. That means the last time Earth was in this same position around the Milky Way, the planet was inhabited not by humans, but by creatures living in a world almost unimaginably ancient to us. Continents were arranged differently. Entire branches of life had yet to emerge. Everything about human history occupies only the tiniest fraction of one galactic orbit. And still, all of that movement, all of that time, all of that vast circular journey, is happening inside only the visible portion of our galaxy. This is why it matters to ground ourselves here first. Because the visible Milky Way is not small. It is already beyond ordinary comprehension. Its spiral disk holds somewhere between 100 and perhaps 400 billion stars, depending on the estimate. Some of those stars are massive and bright, short-lived and dramatic. Most are much dimmer, quieter stars, especially red dwarfs, which are thought to be by far the most common type. The galaxy also contains enormous clouds of gas and dust, star-forming regions, ancient globular clusters, stellar remnants, black holes, neutron stars, rogue planets, and all the subtle debris of billions of years of galactic history. The visible Milky Way is not empty space with a few stars in it. It is a layered, dynamic, and crowded gravitational ecosystem. And yet, even here, it is important not to imagine the stars packed tightly together in the way science fiction sometimes encourages. On the scale of a galaxy, stars are separated by astonishing distances. If you were moving between stars in our local region, you would cross vast emptiness before reaching the next sun. The galaxy is rich with stars, yes, but it is also full of space. Dark, cold, silent space. So much of the Milky Way's visible disk is not a dense swarm in the human sense, but a very spread out pattern of luminous points, gas, and dust crossing a colossal area. This mixture of abundance and emptiness is part of what makes galaxies so hauntingly beautiful. They are full, but also sparse. Structured, but mostly open. Bright in places, and almost impossibly dark in others. From Earth, when we look up under a truly dark sky, we see the Milky Way as a pale band, a misty river of light stretching across the heavens. That band exists because we are inside the galaxy's disk, looking along its plane. We are seeing countless stars blended together into a glow too dense and too distant for the eye to separate individually. In some directions, especially toward the center, the view grows richer and brighter. In other directions, particularly away from the dense central regions, the band softens and thins. This visual experience is deeply human. It has inspired stories, myths, sacred meanings, navigation, poetry. But scientifically, it also tells us something wonderfully concrete. It tells us we are looking through the body of a flattened stellar system from within it. Like an insect trapped inside the wood grain of a vast spinning plank, we do not see the Milky Way from above in daily life. We see it from inside the structure, through the crowded depth of its luminous disk. And that inside perspective can make the galaxy feel harder to grasp. It is often easier to understand an object when you can step back from it. But we cannot step back from the Milky Way in any physical sense. We are inside the thing we are trying to imagine. So astronomers had to reconstruct its form by careful observation, by measuring star positions, gas distributions, motion, and light across many wavelengths. Over time, the picture that emerged was of a barred spiral galaxy, a flattened rotating disk with a central bar-shaped structure and sweeping spiral arms. Even this picture, though, is still only the visible framework. The stellar disk itself is not infinitely thick. Compared with its vast width, it is relatively thin. The thin disk, where many younger stars and much of the gas and dust are found, is only a small fraction of the galaxy's diameter and thickness. There is also a thicker disk component and a central bulge, giving the Milky Way more depth and complexity than a simple pancake. But the overall impression remains. The visible galaxy is a broad flattened disk, not a sphere. That shape matters, because it is the shape most people carry in their minds when they think of the Milky Way. The spiral galaxy, the glowing arms, the central bulge, the starry wheel. And it is a fair image, as far as visible matter goes. But if we are going to understand the true scale of the dark matter around our galaxy, we need to make sure this visible picture is fully felt first. Because what comes next will not replace this image. It will surround it. So let us sit with the visible Milky Way just a little longer. Think about the central bulge, crowded with ancient stars and dominated at its heart by a supermassive black hole, Sagittarius A*, with a mass of about 4 million suns. Think about the spiral arms, not rigid structures like painted lines, but more like regions of greater density moving through the galactic disk, where gas is compressed and stars can form. Think about the enormous nebulae, the nurseries where new stars ignite. Think about the older halo of visible stars and globular clusters that extends beyond the disk. Think about the sun quietly circling in one modest arm spur, taking hundreds of millions of years to complete a lap. All of this is already our home, already vast, already ancient, already enough to make the imagination go still for a moment. And yet, if we are honest, most of us do not really live with this scale in mind. We live at human scale. Streets, rooms, workdays, seasons, commutes, weather, conversations, sleep. The galaxy is too large for the nervous system to hold directly. So when we speak of it, we usually compress it into symbols and familiar phrases. Star system, spiral arm, galactic center. Those phrases make the thing manageable. But behind each one is a level of scale that remains quietly overwhelming. Perhaps that is why slow science has a special kind of power. It gives the mind time to catch up. It allows numbers to turn back into feelings. It allows the impossible to become, not understandable exactly, but at least emotionally present for a moment. 100,000 light years. 27,000 light years from the center. Hundreds of billions of stars. A galactic year longer than human civilization by an absurd margin. This is the visible Milky Way. This is the object many people already regard as an almost incomprehensibly large cosmic home. And it is only the beginning. There is another layer to this that matters deeply for what comes next. Even the visible Milky Way is not defined by a sharp outer wall. It fades gradually. The density of stars drops. The clear brightness of the main disk gives way to weaker outer regions. This matters because it means the galaxy's visible size already involves some interpretation. It is not like measuring the diameter of a coin. It is more like measuring the breadth of a fog bank that slowly thins into darkness. Astronomy often works like that. Nature loves gradients more than lines. And because of that, whenever we speak about the size of the visible Milky Way, we are already dealing with something slightly soft at the edges. Not uncertain in the sloppy sense, but naturally diffuse. Real galaxies do not stop with a perfect rim. They taper. They blend. They leave room for deeper structure to continue beyond what the eye can easily map. That is part of why the dark matter halo was able to remain conceptually hidden for so long. Human beings are drawn to what shines most clearly. If the galaxy fades outward, we are tempted to assume its physical significance fades with it. But gravity does not end where brightness becomes faint. And the hidden mass of the galaxy does not care whether the human eye finds the outskirts photogenic. This is the bridge to the next part. Because once the visible Milky Way has been allowed to feel truly large, only then can the scale comparison do its work. Only then can we ask the question that makes the whole story open up. If the visible stellar disk is already around 100,000 light-years across, then how much larger is the real gravitational structure we are living inside? How far beyond the stars does our galaxy continue? How wide is the unseen body around the glowing disk we call home? That is the moment where the numbers stop being merely impressive and start becoming transformative. If this kind of calm exploration helps you unwind, you can quietly subscribe and return whenever you want another long journey into the universe. And if you feel like it, leave a comment with where you're listening from tonight. There is something peaceful in remembering that everyone hearing these words, wherever they are, is drifting beneath the same visible Milky Way, and inside the same unseen galactic structure. So now we have done the necessary work. We have grounded ourselves in the scale of the visible galaxy first. We have let the stellar disk stand in the mind as something already vast beyond ordinary intuition. We have placed ourselves inside it, far from the center but still deep within its luminous body. We have allowed the visible Milky Way to become not just a phrase, but a real cosmic structure with width, depth, motion, and age. And only now are we ready for the next step. Because the dark halo around our galaxy is not just a little larger than the visible Milky Way. It is larger in a way that changes the meaning of the word galaxy itself. Part 7. So how big is the dark matter halo really? Now we reach the part of the story where the mind has to stretch. Not because the visible Milky Way was small. It was never small. By now, we have already let that truth settle in. A galaxy of stars around 100,000 light-years across is already enough to make ordinary human intuition feel thin and fragile. It is already far beyond anything we are built to picture comfortably. And yet, as immense as the visible Milky Way is, it may still be only the bright inner portion of the real structure we belong to. That is the moment everything changes. Because once astronomers began asking how far the galaxy's hidden mass actually extends, the answer did not come back as slightly larger, or modestly larger, or even a few times larger in a way that feels manageable. The answer came back on a scale that quietly rewrites the meaning of the galaxy itself. So how big is the dark matter halo around the Milky Way really? The most honest answer is that astronomers are still refining it. There is no glowing edge where the halo politely announces its final boundary. Dark matter does not put up a sign. It does not draw a sharp circle around the galaxy and say, "Stop here." The farther out you go, the harder it becomes to define exactly where the halo meaningfully ends and where the wider environment of the local group begins to take over. Nature is not fond of hard edges. But even with that uncertainty, the broad picture is now clear enough to be astonishing. The visible stellar disk of the Milky Way is around 100,000 light-years across. The dark matter halo around it is thought to extend vastly farther, with estimates often reaching out to something like several 100,000 light-years in radius, and in some broader definitions approaching close to 1,000,000 light-years from side to side, or even more when talking about the galaxy's full gravitational domain. In simple language, the hidden structure around the Milky Way is not just a little bigger than the bright galaxy. It may be 10 times, 15 times, perhaps close to 20 times larger than the visible disk, depending on how one defines its edge. That is the kind of scale change that stops sounding like a correction and starts sounding like a revelation. It means that the glowing Milky Way most people imagine, the graceful spiral of stars with its bright arms and crowded center, may occupy only a relatively small central region inside the galaxy's true dark gravitational body. The galaxy we notice is not the whole galaxy. It is the lit middle. Imagine for a moment that the visible Milky Way were shrunk down to the size of a dinner plate sitting on the floor of a large room. Not a tiny plate, but a good-sized dinner plate. Already, on that scale, the solar system becomes almost absurdly small. But the dark matter halo would not stop at the edge of the plate. It would not even stop at the edge of the table beneath it. It would spread outward through the room, past the furniture, past the walls, out into the wider building, defining a much larger invisible space within which the bright plate sits quietly at the center. Or think of it another way. Imagine a lantern glowing in the middle of a very large dark valley. If you know only the lantern, you might think the light defines the place. But then you begin measuring how the wind moves, how the ground slopes, how water gathers, how echoes behave, and you realize the valley is vastly larger than the patch of light. The lantern is real, yes. Beautiful, yes. But it is not the thing that defines the true shape of the land. That is what the dark halo does to our understanding of the Milky Way. It does not erase the visible galaxy. It enlarges it into something deeper and stranger. And perhaps the most surprising part is not only the width, but the fact that we live so comfortably inside this enormous hidden structure without ever noticing it directly. We tend to think of ourselves as people living on a planet, orbiting a star, inside a galaxy. That is all true. But the dark halo adds another layer. We are not only inside a galaxy of stars. We are inside a gigantic, mostly invisible mass distribution that stretches far beyond the stars we can see. Our local star system is not near the edge of the Milky Way's real gravitational domain. It is deep inside it. Deep. That word matters. Because when you stand under the night sky and look at the pale river of the Milky Way, it is natural to imagine yourself looking toward the main body of the galaxy, perhaps surrounded by its stars but still somehow apart from it as an observer. In reality, we are embedded in the system much more completely than that. The visible stars around us are only part of the environment. The dark halo is the wider environment, silent and unseen, through which the Sun and Earth have been moving for their entire existence. And how do scientists arrive at these enormous scale estimates? Slowly, indirectly, patiently. They look at the motions of objects far beyond the bright stellar disk, distant globular clusters, satellite galaxies orbiting the Milky Way. The way these smaller companions move tells astronomers something about how much mass must be present to govern those motions. If the galaxy's gravitational reach were limited mostly to the visible disk, then those distant companions would not behave the way they do. But many of them move as though they belong to a much larger and heavier system. It is one of the most elegant things about astronomy. The invisible is mapped through the visible. A dwarf galaxy orbiting far from the Milky Way's bright center becomes a kind of gravitational probe. A globular cluster out in the halo becomes a clue. Each distant object is like a buoy floating in a dark ocean, telling us something about the shape of the currents beneath. And all of these clues, taken together, suggest that the Milky Way's gravitational body extends astonishingly far beyond the stars. This is also where a very useful distinction appears. There is the visible Milky Way. Then there is the Milky Way as a gravitational system. Those are not the same thing. The visible Milky Way is what shines. The disk, the bulge, the spiral arms, the gas and dust we can detect directly. But the Milky Way as a gravitational system includes the dominant dark matter halo, which shapes the motion of everything inside it and defines a much larger sphere, or at least a much larger extended region, around the luminous galaxy. And if that is true, then the familiar phrase "our galaxy" has been underselling the reality all along. Because the thing we call our galaxy is less like a pinwheel of stars in empty space and more like a vast dark realm with a bright pinwheel glowing near its center. The emotional effect of that is hard to overstate. It means the galaxy is not where the stars stop. It is where the gravity continues. That single shift in wording changes everything. Children grow up seeing pictures of spiral galaxies and naturally conclude that the bright disk is the galaxy. Adults do too, really. It is an understandable simplification. But the deeper truth is more interesting. The stars are simply the part of the galaxy that is easiest to see. They are not necessarily the part that tells you where the galaxy really ends, or even what most of it is made of. That is why the dark halo feels so philosophically unsettling. It tells us that the galaxy's true scale is not written mainly in light. It is written in gravity. And gravity, unlike light, does not care whether human eyes are impressed. Now, there is some uncertainty in the exact size because the halo does not have a clean visible boundary. Different scientific definitions can emphasize slightly different things. Some discussions focus on the denser inner halo, where the Milky Way's own dark matter clearly dominates. Others talk about a broader virial radius, a kind of practical gravitational boundary within which the system is considered bound in a certain cosmic sense. And still others consider the way the Milky Way's influence blends into the wider environment shared with nearby galaxies. But the takeaway remains the same whichever estimate you prefer. The dark halo is enormous on a scale that dwarfs the visible disk. If the disk is 100,000 light-years across, and the halo reaches hundreds of thousands of light-years outward, then what we are dealing with is not a minor extension. It is a hidden expansion of the galaxy's size so large that the visible Milky Way becomes, by comparison, almost like a glowing city at the center of a vast invisible country. That image helps, I think. A city is important. It is where the lights are, where the energy is obvious, where the eye is drawn. But the country around it may be much larger, quieter, less visible from a distance, and no less real. The dark halo is like that larger territory. It does not sparkle. It does not call attention to itself. But it defines the full domain. And there is another important dimension to this scale. Mass. The Milky Way's visible matter, the stars, gas, dust, planets, everything ordinary, is thought to add up to something like tens of billions to perhaps around 100 billion solar masses, depending on how one totals the visible components. That is already huge beyond everyday comprehension. But the full Milky Way, once the dark halo is included, may weigh around 1 to 2 trillion times the mass of the Sun. Trillion. That word is so large it barely feels attached to anything real. And yet here it is, attached to our home galaxy. What that means in ordinary language is that most of the galaxy's mass is not in the bright stars. Most of it is in the invisible halo. The stars are the glow. The dark halo is the weight. And once you understand that, the visible Milky Way starts to feel strangely delicate. Not small, but delicate. Like a filigree of light resting inside a much heavier unseen form. A frost pattern on the surface of a window whose full structure extends beyond the decorated glass. Something beautiful, but not the main load-bearing component. This is where the story becomes very peaceful in its own odd way. Because the night sky stops feeling like scattered lights hung in emptiness. It begins to feel supported, held, structured by something vast and silent beneath it. When you look toward the stars of the Milky Way, You are not looking at a fragile luminous object floating by chance in darkness. You are looking into the inner bright region of a galaxy anchored by an immense dark framework. The stars do not hang in space with no deeper support. They move within a giant gravitational field that extends far beyond what you can see. That means our entire solar system is like a tiny passenger inside an enormous invisible ship. We do not feel the ship directly. We live our lives on one small deck. We watch the local lights. We track the nearby weather. But the ship itself extends much farther than our senses suggest, and it is carrying all of us through the cosmic night. It is difficult to grasp scale like this without comparison, so let us return to feeling rather than numbers. If the visible disk of the Milky Way is already enough to overwhelm the mind, then the dark halo is the part that makes the mind go quiet. Because it reveals that even our largest familiar cosmic home is only partly visible. It reveals that the real Milky Way is not an object we merely observe from within, but an enormous hidden environment surrounding us on all sides. And it reveals that for most of human history, when people looked up and imagined the galaxy, they were seeing only a small luminous fraction of the real thing. There is a kind of tenderness in that realization. Human beings have always built meaning from what they can see. Constellations, stories, calendars, myths, navigation, beauty, wonder. And all the while, the main gravitational body of our galaxy was present but unnoticed, shaping everything anyway. The invisible giant did not need our awareness to do its work. It held the galaxy together long before anyone named it. It carried the Milky Way through time long before telescopes, long before science, long before the first human eyes ever looked into the dark and wondered what home really was. That gives dark matter a strangely ancient feeling. Not ancient in the sense of old ideas, but ancient in the sense of having been there before our understanding, before our language, before our categories. It reminds us that reality is not obliged to become real only once we discover it. The halo was there all along, and its scale was there all along too. Now, one of the most powerful consequences of this scale is that the Milky Way's halo reaches well into the territory we might casually call intergalactic space. The stars thin out, yes. The bright disk ends, yes. But the gravitational structure continues. That means the distinction between galaxy and the space around galaxy becomes more subtle than it first seems. The visible galaxy may feel local, while intergalactic space feels remote and separate. But the dark halo blurs that intuition. It extends the Milky Way's presence far into regions where starlight no longer tells the full story. The galaxy, in that sense, is reaching into darkness much farther than the eye expects. And that is where the next part of the story naturally leads. Because once you realize how large the dark halo is, the next question becomes irresistible. What lies in those outer reaches? What does it mean for our galaxy's hidden structure to stretch so far into what looks, to us, like empty space? Where does the Milky Way end, really, if its gravity continues long after its stars have faded from view? If these slow journeys through the universe help you relax, you can gently like the channel, subscribe for more, or leave a quiet comment about where you're listening from tonight. It is a comforting thought that people across Earth are all tucked inside the same vast dark halo, even if none of us can see it directly. So let the scale settle in now. The visible Milky Way is around 100,000 light-years across. The dark matter halo surrounding it is vastly larger, stretching outward for hundreds of thousands of light-years and defining a galactic structure far bigger than the bright disk alone suggests. This hidden halo contains most of the galaxy's mass. It surrounds the stars. It holds the system together. It reaches far beyond the part of the Milky Way the human eye could ever mistake for the whole. And once that truth lands, the galaxy is never quite the same again. It is no longer just a river of stars across the sky. It is a great invisible kingdom, with a narrow band of starlight glowing near its center. Part 8, the halos reach into intergalactic space. There is a moment in this story where the galaxy stops feeling like an object and starts feeling like a territory. That is the threshold we are crossing now. Because once you accept that the Milky Way is not just the bright disk of stars we can see, but a far larger structure wrapped in dark matter, a new and very strange question begins to rise. If the halo stretches hundreds of thousands of light years beyond the visible galaxy, then what exactly lies out there in those outer regions? What is that space? Does it still belong to the Milky Way? Or have we already entered something else entirely? At first, the instinct is to say that beyond the bright stars must be emptiness. That feels natural. Human beings are visual creatures. We trust what glows. So when the visible disk fades, we tend to assume the galaxy is fading with it. We imagine a fairly simple scene. First the stars, then the edge, then the dark between galaxies. But the dark matter halo quietly tells us that the real picture is not so simple. The galaxy does not end where the starlight thins out. Its hidden body keeps going. Its gravity keeps reaching. Its influence continues into what, to the eye, would look like open intergalactic dark. And that is one of the most beautiful corrections modern astronomy has given us. It teaches us that the space around a galaxy is not as empty, cleanly separated, or emotionally distant as it first appears. The Milky Way does not sit like a little island of light in an otherwise untouched sea. It is surrounded by a much larger invisible realm, and that realm stretches well out into the darkness between the great visible structures we are used to picturing. To feel this properly, it helps to imagine standing at the shoreline of an ocean at night. You can see the surf near your feet. You can see perhaps a little farther where the moonlight catches the water. Beyond that, the sea seems to vanish into blackness. But the ocean has not ended where your eyes stop being useful. It continues into darkness with the same reality it had near the shore. Your sight fails first. The water does not. That is a little like what happens with the Milky Way. The stars are like the moonlit surface near the shore. They are what we can notice. They are what define the scene for us emotionally. But beyond the bright region, the galaxy's deeper gravitational reality continues into darkness. The visible galaxy fades before the hidden structure does. And once you understand that, the phrase intergalactic space starts to feel less absolute. Because what do we really mean by the space between galaxies? Do we mean the regions with no stars? No bright gas clouds? No visible spiral arms? If so, then yes, much of the outer dark halo occupies territory that feels intergalactic to the eye. But if we mean a place where the Milky Way no longer has any meaningful presence, then the answer becomes more subtle. The galaxy's presence, through its dark matter halo, reaches much farther than its visible light suggests. This means that the outer halo is a kind of threshold region, not the bright city center of the galaxy. Not yet the totally separate domain of some distant major galaxy either, but a quieter, dimmer, more invisible extension of our own galactic home. A place where the Milky Way is still present, even though it no longer announces itself with brilliance. That is such a different way of imagining our place in the universe. Most of us grow up with clean diagrams. A galaxy here, another galaxy there, black emptiness in between. The images are useful, of course, but they can hide how gradual nature often is. They can make cosmic structure feel more sharply separated than it really is. In truth, galaxies can have diffuse outskirts, faint stellar halos, streams of torn-apart stars, orbiting dwarf companions, clouds of hot gas, and enormous dark matter distributions reaching far beyond the obvious bright disk. The Milky Way is not an isolated pinwheel with a hard border. It is more like a great luminous center with a hidden gravitational atmosphere extending outward into the dark. That word atmosphere is not technically exact, but emotionally it helps. Not an atmosphere of air, of course. Not something you could breathe or feel on your skin, but an extended surrounding domain. a region of influence, a broad hidden envelope that softens the line between galaxy and the larger cosmos. And this outer region is not simply empty. That matters. Because when people hear that the halo reaches into intergalactic space, they may picture a vast invisible blob doing nothing at all. But the outer halo is not meaningless dark. It is part of a larger galactic environment. The Milky Way has companions there. Small satellite galaxies orbit within its gravitational reach. Ancient globular clusters travel through these outskirts. There are stellar streams, the faint remnants of smaller systems that ventured too close and were slowly stretched apart by the galaxy's gravity. There is hot gas in the broader galactic surroundings. There is structure, motion, history. The outer reaches may be dark, but they are not lifeless in the cosmic sense. They are a quiet borderland, full of clues. In fact, some of the best evidence for the halo's scale comes precisely from these distant companions. Tiny dwarf galaxies, much smaller than the Milky Way, orbit around it like cautious satellites around a giant unseen mountain. The Large and Small Magellanic Clouds are the most famous examples visible from the southern hemisphere, though they are only part of a larger family of dwarf companions. These little galaxies are not simply wandering nearby by coincidence. They are part of the Milky Way's gravitational story. Their motions help reveal how far the galaxy's hidden mass extends. It is a lovely thought, really. Small galaxies moving through darkness, helping us measure the invisible shape of the larger one they orbit, like lantern boats drifting on black water, telling us where the current must be. And this is where the outer halo begins to feel less abstract, because it is not just a mathematical extension on a graph. It is a real region where things happen. It is where smaller galaxies can be captured, held, distorted, or slowly consumed. It is where the Milky Way's past mergers leave faint traces. It is where the galaxy's history lingers in long invisible architecture. You could almost think of it as the Milky Way's memory zone. The bright disk contains much of the ongoing visible life of the galaxy, the stars, the gas, the familiar structure. But the outer halo carries a quieter record. It remembers ancient encounters. It remembers swallowed companions. It remembers the slow work of gravity over billions of years. And because it stretches so far outward, it also changes our emotional sense of isolation. We often imagine ourselves deep inside a galaxy, yes, but the galaxy itself is frequently imagined as a clearly bounded object in the darkness. Once the halo comes into view, even conceptually, that isolation begins to soften. The Milky Way starts to feel less like a sharp island and more like a large domain with outskirts that blend gradually into a wider cosmic neighborhood. That blending is important, because the universe is built from relationships, not just isolated objects. Stars belong to galaxies. Galaxies belong to groups. Groups belong to larger structures. And dark matter is part of the hidden scaffolding that helps define these relationships on every scale. So when the Milky Way's halo reaches into what looks like intergalactic space, it is doing more than simply increasing the galaxy's size. It is reminding us that cosmic structure is layered and continuous. The visible parts are not the whole. The spaces between visible things are not always empty. The darkness has shape in it. That phrase might be the heart of this part. The darkness has shape in it. Not shape in the way a mountain has a sharp silhouette against the sky, but shape in the deeper physical sense. Distribution, weight, influence, structure. The kind of shape you learn not by sight, but by motion. And there is something very peaceful in that idea. Because it means the universe is less like scattered islands in a void and more like a connected terrain whose true structure is partly hidden from direct view. The visible stars are like campfires on a vast nighttime landscape. But the hills, valleys, ridges, and plains of that landscape exist whether or not the firelight reaches them. Dark matter halos are part of that larger terrain. Now, let us pause for a moment and think about distance in a more human way. If the visible Milky Way already takes 100,000 years for light to cross, and the dark halo extends hundreds of thousands of light years farther into space, then the outer halo is not some thin fringe near the edge of the familiar galaxy. It is a huge region in its own right. A region so large that if our sun were somehow moved around within different parts of it, we might still feel entirely inside the Milky Way's gravitational environment even while being unimaginably far from the bright stellar disk we know. That is worth sitting with. The outer halo is not just the edge. It is a vast country. A dark, mostly invisible country surrounding the visible city of stars. And if you were there, far out in those outer reaches, the night sky would feel very different. The Milky Way's bright disk would not wrap around you in the same familiar way. The density of nearby stars would be much lower. The galaxy's visible body might appear more distant, more concentrated in one direction, less like a place you are inside and more like a glowing structure somewhere deeper inward. Yet gravitationally, you could still belong to the same galactic system. That is the strange thing about hidden scale. It changes what it means to be inside something. We tend to assume being inside means being surrounded by obvious visible walls, obvious features, obvious signs of belonging. But the halo shows that belonging can be gravitational. A region can still be part of the Milky Way even when it no longer looks like the star-filled galaxy we instinctively imagine. And that helps us approach one of the most beautiful scientific truths of all. A galaxy is not only what it looks like. A galaxy is what it holds, what it binds, what it influences, what remains within its deeper gravity. This is why the outer halo reaching into intergalactic space is not just an interesting footnote. It changes the very boundary of home. It means our galaxy extends far beyond the part ancient skywatchers could see. It means that when we say we live in the Milky Way, we are talking about an invisible environment vastly larger than the ribbon of stars crossing the sky. And perhaps there is something comforting in that expansion of home. Human life is so local. Rooms, streets, cities, routines, small concerns. Even our planet is tiny on cosmic scales. Yet around us, without drama, without light, without announcement, stretches this immense hidden structure that has held our galaxy together for billions of years. It reaches into the dark between visible things. It extends outward in silence. It reminds us that our home is larger than our eyes can report. That does not make us less small, exactly. But it does make our smallness part of something more majestic. There is also a lovely tension here between emptiness and belonging. The outer halo is sparse, extremely sparse. If you imagine stars scattered through these outskirts, they are far apart. If you imagine matter in the ordinary sense, there is not much of it. It is not crowded like the inner galaxy. It is not full of bright spiral structure. In many ways it is quiet, dark, and nearly empty. And yet, despite that sparseness, it still belongs to the galaxy's structure. It is still part of the whole. That feels emotionally resonant somehow. The universe is teaching us that something can be quiet and still matter. Something can be dark and still define the shape of a home. Something can be almost invisible and still do most of the holding. And once that lesson settles in, the next thought comes almost automatically. If the Milky Way's hidden halo reaches so far outward, then what about other galaxies? What about Andromeda, our great neighboring spiral galaxy? Does its dark halo reach outward too? And if both halos extend so far into the surrounding dark, what happens where those invisible territories approach one another? This is where the story begins to widen again. Because the halo does not only tell us that the Milky Way is larger than its stars. It tells us that our galaxy is part of a larger gravitational neighborhood, one where the invisible structures of major galaxies may already be interacting long before their visible disks ever meet. If this slow walk through the hidden universe is helping you relax, you can quietly subscribe and stay with the journey. And if you feel like it, leave a comment with where you're listening from tonight. It is a beautiful thing to imagine so many people, in so many places, resting inside the same invisible galactic domain while thinking about how far their home truly reaches. So let this part settle gently. The dark halo around the Milky Way stretches outward into regions that, to the eye, would seem like ordinary intergalactic darkness. In those far reaches, the visible stars no longer define the boundary of the galaxy. Gravity does. The Milky Way still has a presence there. It still holds companions there. It still carries its hidden mass there. The galaxy continues into silence long after the light has begun to fade. And once you understand that, you begin to see the cosmos differently. Not as bright things floating in emptiness, but as visible islands rising from a much larger invisible landscape. Part 9, where our halo meets the bigger cosmic neighborhood. At a certain point, the story of our galaxy stops being only the story of our galaxy. That is where we are now. Because once the Milky Way's dark halo has been allowed to grow to its true scale in the imagination, once it has stretched far beyond the bright disk and into the quiet dark around it, another thought begins to arrive almost by itself. If our galaxy's hidden structure extends that far, then surely other galaxies must have their own dark halos too. And if that is true, then the universe becomes stranger again. Because galaxies are no longer just separate islands of stars scattered through empty space. They become great invisible realms, each with a glowing center and a much larger hidden body around it. And once you begin thinking that way, it becomes much harder to believe those realms are always cleanly isolated from one another. Sometimes they must approach. Sometimes they must overlap. Sometimes they must already be influencing one another long before their bright stars ever come close. That idea changes the emotional map of the cosmos. It means the Milky Way is not simply sitting alone in the dark with its own private halo. It belongs to a larger galactic neighborhood, a quiet community of galaxies bound together by gravity. Astronomers call this neighborhood the local group, and while the name sounds modest, the scale is anything but small. The local group is a collection of more than a few dozen galaxies, depending on how one counts the faintest and smallest members. Most are tiny dwarf galaxies, dim and delicate compared with the major spirals. But two great galaxies dominate the group in both mass and presence. One is our own Milky Way. The other is Andromeda. Andromeda has fascinated people for a very long time, though for most of human history it was only a faint smudge in the sky, visible to the naked eye under dark conditions. It did not look like a galaxy at all. It looked like a patch of dim mist. Only later did we understand what it really was, a vast spiral galaxy, the nearest major galaxy to our own, containing perhaps around 1 trillion stars, or something in that general order depending on how one estimates. In any case, it is enormous. So enormous that if human eyes were sensitive enough to see its full bright extent clearly, it would appear many times wider than the full moon in the sky. And yet, even Andromeda's visible glory is not the whole story. Like the Milky Way, it too appears to sit inside a vast dark matter halo. And that is where things become especially interesting. Because the Milky Way and Andromeda are not separated merely by empty black distance in the simple way old textbook diagrams might suggest. They are separated by about 2.5 million light-years of space. Yes, that is still a colossal gulf. But if both galaxies possess enormous dark halos extending hundreds of thousands of light-years outward, then their invisible domains begin to feel less like sharply distinct kingdoms and more like neighboring territories in a wider gravitational landscape. This is one of the most beautiful lessons in the whole story of dark matter. The visible universe teaches us separation. Bright galaxy here, another bright galaxy there, darkness in between. But the hidden universe teaches us continuity. Gravity reaches farther. Structure extends deeper. The boundaries we first imagine are often more porous and gradual than they appear. The Milky Way and Andromeda are not just two bright spirals looking at each other across empty space. They are two immense gravitational systems already participating in a shared future. And perhaps, in some broad sense, already participating in a shared present. That shared present unfolds inside the local group, which is itself held together by gravity over millions of light years. You can think of it as a kind of family of galaxies, though even that may feel too warm and close for the vast silence of cosmic scales. Still, the metaphor helps. The Milky Way is not an isolated wanderer. It belongs to a group. It has companions, rivals, future merger partners, smaller followers. And that whole arrangement makes more sense once dark matter is included, because the group's stability and long-term behavior depend not only on the stars we see, but on the huge invisible masses each galaxy carries around it. Without the dark halos, the local group would not feel the same. Its dynamics would not work the same way. Its future would not unfold the same way. This is why the Milky Way's halo meeting the bigger cosmic neighborhood matters so much. It is not only about scale for its own sake. It is about relationship. It is about realizing that our galaxy's hidden mass does not merely support the stars inside it. It also helps determine how our galaxy moves among other galaxies. And those other galaxies are not theoretical dots on a chart. They are real places, real structures, real cosmic companions. The large and small Magellanic Clouds, for example, are visible from the southern hemisphere as soft patches of light. They are dwarf companion galaxies of the Milky Way, and they are moving through our larger galactic environment under the influence of the Milky Way's gravity. Over time, such smaller galaxies can be distorted, stripped, captured more deeply, or even merged into the larger system. The Milky Way's history includes this kind of quiet cannibalism. It has grown partly by feeding on smaller companions over billions of years. That fact alone makes the galaxy feel more alive. Not alive in the biological sense, of course, but alive in the sense of dynamic history. It has not existed as a frozen static object. It has changed. It has absorbed. It has wandered through time gathering mass, collecting stars, reshaping its outskirts. Some of the stellar streams found in the Milky Way's halo are likely the stretched remains of smaller galaxies or clusters torn apart by our galaxy's gravitational pull. And that means the outer halo is not only an invisible extension, it is also a record of past encounters, a memory field, a borderland where the remains of old relationships still drift. And if the Milky Way can do that to smaller galaxies, then what happens when two giants approach each other? That is where the story naturally turns toward Andromeda. Because Andromeda is not merely another galaxy in the local group. It is, in some sense, our great counterpart. Larger in visible size than the Milky Way by many estimates, though the exact comparison depends on what one measures. Massive, spiral, ancient, surrounded by its own satellites, embedded in its own dark halo, and, perhaps most importantly, moving toward us. The Milky Way and Andromeda are on a long collision course. That statement can sound alarming at first, but cosmic time softens everything. This is not a near-term event. The likely merger lies billions of years in the future, often described as roughly 4 to 5 billion years from now, though the details can shift as measurements improve. For human life, for civilization, for even the long duration of our species if we imagine it generously, this is unimaginably distant. And yet, on galactic timescales, it is a real and shaping future. Two giant spiral galaxies in the same local group, drawn toward one another by gravity, each carrying not only stars and gas but also immense dark halos, slowly approaching across cosmic time. What is so fascinating is that the visible disks do not need to touch for the relationship to begin mattering. Their invisible halos extend outward far beyond the bright stars. In a very real sense, The merger story begins in darkness before it becomes visible in light. That is such a striking idea. The first contact between galactic giants is not a clash of spiral arms. It is a meeting of invisible mass. A deep gravitational conversation carried out in silence long before the luminous centers fully interact. And once you start imagining galaxies this way, it becomes much harder to think of them as simple objects. They feel more like weather systems, or empires, or drifting continents with long invisible coastlines. Their visible parts are dramatic, yes, but the deeper story is carried in the unseen mass around them, shaping their motion and preparing their future. The Milky Way's dark halo, then, is not just a hidden shell around our home galaxy. It is part of how our galaxy participates in the architecture of the local group. It helps determine how we tug on Andromeda. It helps determine how dwarf galaxies orbit us. It helps explain why the neighborhood has the structure it does. And that leads to a humbling realization. When we ask where our galaxy ends, the answer may not be fully meaningful unless we also ask where our neighborhood begins. Because the more we learn about dark matter halos, the more the boundaries between objects begin to blur into relationships. The Milky Way has a halo. Andromeda has a halo. The local group has a shared gravitational life. Smaller galaxies move inside this broader arrangement. Over immense spans of time, matter flows, merges, and reconfigures. The universe is not made of perfectly isolated luminous things. It is made of structures nested within larger structures, many of them invisible except through gravity. This nesting is one of the deepest patterns in cosmology. Planets orbit stars. Stars belong to galaxies. Galaxies belong to groups. Groups belong to larger filaments and clusters. And dark matter appears again and again as the hidden framework making that nesting possible. That is why the Milky Way's halo meeting its cosmic neighborhood is not a side issue. It is the beginning of a larger perspective. It tells us that to understand our galaxy fully, we must stop thinking only inward and begin thinking outward. Outward toward Andromeda. Outward toward the local group. Outward toward the invisible scaffold linking one great structure to the next. There is also something emotionally beautiful about this. We often think of home as something bounded, something with walls, edges, a clear inside and outside. But cosmic home is much stranger than that. The Milky Way is our home galaxy, yes, but its hidden structure reaches outward into a wider community. Our home is part of a neighborhood. Our neighborhood is part of something larger still. The deeper we look, the less complete any one boundary seems. That can feel disorienting at first, but it can also feel comforting, because it means the universe is not just fragmented into lonely pieces. It is held together by relationships. Gravity makes neighbors out of distant things. Dark matter makes structure out of what would otherwise feel like scattered light. And in that sense, the universe becomes less like a silent gallery of separate paintings and more like a single woven fabric, with visible stars as the embroidery and dark matter as much of the thread. Now, let us linger for a moment on Andromeda itself, because it deserves that attention. 2.5 million light-years away, it is still close enough, in galactic terms, to be our major neighbor. Light leaving Andromeda tonight will travel for 2.5 million years before reaching us. That means every photograph of Andromeda is a view into the deep past. We never see it as it is now in any immediate sense. We see an ancient version of it, and the same is true in reverse. If there were observers in Andromeda studying the Milky Way, they would see our galaxy as it was millions of years ago. That time delay alone makes the cosmic neighborhood feel dreamlike. Even nearby galaxies are not truly nearby in the ordinary sense. The neighborhood is real, but it is stretched through time as well as space. Still, despite that delay, gravity links these galaxies in the present. The mutual pull does not care about human emotional distance. The local group evolves according to mass, motion, and time. The Milky Way and Andromeda are approaching one another, carrying their halos, carrying their stars, carrying their invisible weight toward a future merger that will reshape both. When that merger eventually happens, the night sky from whatever remains of the solar system, if anything remotely like our system remains in place by then, would become extraordinary. Andromeda would swell in brightness over eons. Tidal distortions would grow. Great arcs and flows of stars would be pulled through space. The two spiral galaxies would gradually lose their neat forms and settle into a new larger galaxy, likely more elliptical in appearance. But again, what matters for our present story is not the visible fireworks. It is the invisible preparation. The halo meeting the halo. The gravitational fields beginning to dominate the relationship long before the visible disks fully intertwine. That is where the true larger neighborhood reveals itself. And that larger neighborhood may itself sit inside even bigger structures. The local group is part of a broader region of galaxies, itself embedded in the cosmic web, that enormous large-scale network of filaments, clusters, and voids shaped in large part by dark matter over cosmic time. So when we widen our perspective enough, the Milky Way's halo becomes just one level in a grand hierarchy of hidden structure. That hierarchy is both thrilling and calming. Thrilling because it keeps expanding the story beyond what we thought was large. Calming because it reminds us that scale in the universe is not chaotic. It is patterned. There are layers. There is architecture. There is a kind of quiet order hidden beneath the visible brightness. Perhaps that is why dark matter captures the imagination so deeply. It does not merely add mystery. It adds coherence. It suggests that the visible universe rests on a deeper framework. A galaxy is not just stars. A group is not just a list of galaxies. A cosmic neighborhood is not just objects floating randomly near one another. Beneath all of it there is hidden mass shaping the dance. If this gentle walk through the universe is helping you relax, you can quietly leave a like, subscribe, or share a comment about where you're listening from tonight. It is always lovely to imagine people across different cities and countries winding down under the same Milky Way, all of us carried by the same unseen galactic structure. All of us part of the same larger cosmic neighborhood. So let this part settle now. The Milky Way's dark halo does not exist in isolation. It belongs to a wider gravitational world. Our galaxy shares the local group with Andromeda and many smaller companions. These galaxies are not simply bright islands in separate pools of darkness. Each carries a larger hidden body of dark matter. And those bodies shape how the galaxies move, merge, and belong to one another. The future collision between the Milky Way and Andromeda begins not with stars, but with invisible mass. The deeper reality of the neighborhood is written in gravity first, and light second. And once you understand that, home begins to feel larger again. Not just a galaxy. Not just a dark halo. But a place inside a wider family of great invisible structures, all drifting together through the long silence of the cosmos. In the final part, all of this comes back to us in the most personal way. Because after the scale, the mystery, the halos, the neighbors, and the cosmic architecture, one quiet thought remains. What does it mean that we live inside something this large, this hidden, and this strange? Part 10. What it means to live inside something we cannot see. By the end of a journey like this, the facts begin to feel like more than facts. They begin to feel like a change in atmosphere. Not because the universe itself has changed while we were looking at it, but because our place inside it has quietly shifted. Or rather, our understanding of that place has shifted. The sky above us is still the same sky. The Milky Way still spreads across the darkness on clear nights. The stars still rise and set in their patient ways. The Earth still turns. The Sun still carries us in its long orbit around the galactic center. And yet something is not the same. Because now, when we think of our galaxy, we no longer think only of the shining disk. We no longer imagine home as a bright pinwheel of stars and little else. We have followed the clues, one by one, from the strange motion of outer stars to the idea of hidden mass, from the need for an unseen halo to the astonishing scale of that halo, from the visible Milky Way to the larger gravitational realm around it, from our own galaxy to its wider cosmic neighborhood. And now, after all of that, a quieter question remains. What does it mean that we live inside something this large, this hidden, and this strange? That is not a question with a single neat scientific answer. Science can tell us what the evidence suggests. It can tell us how stars move, how galaxies hold together, how dark matter seems to shape the cosmos. But meaning is a slightly different thing. Meaning lives at the edge where knowledge meets feeling. It begins where facts stop being separate and start forming a worldview. And I think the first meaning dark matter gives us is humility. Gentle humility, not harsh humiliation. The kind that softens the ego rather than wounds it. For most of human history, people naturally trusted what they could see. And why wouldn't they? The visible world is how we survive. Light tells us where the ground is, where the horizon is, where home is, where danger is, where the faces of people we love are. Seeing has always been one of the great foundations of human experience. So it is deeply humbling to discover that on the scale of the universe, the visible may be only a small fraction of what matters most. That what shines is not necessarily what dominates. That the stars, as beautiful and emotionally central as they are, may be only the luminous surface of a much greater hidden reality. There is something wonderfully corrective in that. It reminds us that the universe is under no obligation to arrange itself around human intuition. It does not simplify its deepest truths for our convenience. It allows us to notice what we can notice first, and then, if we are patient enough, it invites us further. That is what dark matter feels like to me. An invitation further. Further than the eye. Further than first impressions. Further than the easy belief that what is visible must also be what is most important. In that way, dark matter is not just an astrophysical mystery. It is almost a lesson in perception. A lesson in how limited our first glance can be, and how much larger reality becomes when we learn to infer rather than merely observe. Because that is how we came to this hidden halo in the first place. Not by seeing it directly, but by noticing its consequences. The stars moved as though something else was there. The galaxy held together as though something else was there. Distant companions orbited as though something else was there. Light bent, structure formed, motions continued, all as though something unseen was doing most of the holding. And that may be the second meaning dark matter offers us. The hidden can still be real. That sounds obvious at first, almost too simple to mention, but it is worth lingering on. Human beings often confuse invisibility with absence. If something does not announce itself in the usual way, we assume it is not significant. But the universe keeps offering a gentler truth. Some of the deepest structures are not visible structures. Some of the strongest supports are not the ones that glitter. Some of the realities doing the most work remain quiet. The Milky Way itself teaches us that now. Its bright stars are what we notice. Its dark halo may be what makes the whole system possible. And there is something almost comforting in that. We live in a culture that often rewards display, brightness, speed, noise, immediate proof of presence. But the cosmos seems to be built, at least in part, on something different. A vast silent scaffold, a hidden mass, a structure that does not ask to be admired, and yet holds everything together anyway. Perhaps that is why this topic can feel unexpectedly peaceful. Dark matter does not just make the universe stranger. It makes it deeper. It tells us that not all foundations are visible. And then, of course, there is scale. Once the dark halo is allowed into the picture, the Milky Way becomes far larger than the bright galaxy we once imagined. The visible disk is already immense. 100,000 light-years across. Hundreds of billions of stars. A scale that already pushes the mind almost to the point of surrender. But then comes the hidden extension. The dark matter halo reaching hundreds of thousands of light-years farther, perhaps defining a galactic structure vastly larger than the starlit one. That kind of scale does something unusual to the human mind. It does not merely impress it, it quiets it. There are some ideas that produce excitement, and others that produce a kind of hush. This is one of the hush-producing ones. Because when home suddenly becomes that large, when you realize you are not merely on a planet around a star inside a visible galaxy, but inside a massive invisible halo whose true extent far exceeds the bright Milky Way of human imagination, there is almost nothing to say for a moment. Only wonder. Only a kind of spaciousness inside the mind. And that spaciousness can be restful. We spend so much of life inside small scales. A room, a message, a schedule, a worry, a conversation replaying in the mind late at night. Human life narrows around immediate things because immediate things matter to survival. But cosmic thinking, especially slow cosmic thinking, has a different effect. It gently widens the frame. It reminds us that our lives, while precious, unfold inside something immeasurably larger and older than any single fear or deadline. That does not erase the human world, but it can soften its sharpest edges. And perhaps that is part of why the night sky has always calmed people, even before science explained what they were seeing. Something in us responds to scale. Something in us loosens when the frame widens. Dark matter widens the frame even more. It tells us that the sky is not merely full of visible stars. It tells us the galaxy itself is larger than the stars reveal. It tells us our home has an unseen depth. And once you understand that, the word home begins to feel different too. Because home is usually imagined as something enclosed. A house, a room, a city, a nation, a planet, perhaps, if we think a little bigger. But now home becomes a galaxy, and not even just a galaxy of light. It becomes an invisible gravitational realm stretching far beyond what our ancestors could have imagined. That is a very strange kind of home. A home without walls. A home we cannot directly see. A home defined partly by hidden mass and ancient motion. A home that does not need our awareness to hold us inside it. And yet it is home all the same. The earth is inside it. The sun is inside it. Every tree, every ocean, every sleeping animal, every human memory, every language ever spoken, every song, every argument, every first love, every farewell, every city ever built, every child ever carried, every quiet room in the middle of the night, all of it exists inside this enormous unseen galactic structure. That thought has a way of making the familiar feel both smaller and more sacred. Smaller, because it reminds us how local we are. More sacred, because it reminds us how improbable and delicate conscious life is inside such a vast and silent architecture. There is another meaning here too, and it may be the most moving one. We belong to realities we do not fully understand. That is not a failure. That is the human condition. Long before anyone knew about galaxies, human beings lived inside one. Long before anyone suspected dark matter, humanity was already held by it. Long before any telescope measured the motion of stars in distant spirals, the Milky Way's halo was already there, already shaping the galaxy, already carrying our solar system through the dark. We do not need full understanding in order to belong. We belonged first. Understanding came later. And slowly. That may be one of the most reassuring truths in science. Discovery does not create reality. It reveals it. The universe does not wait for us to name it before it becomes real. It simply is. Patiently. Quietly. Indifferently, perhaps, but also beautifully. And we, for our brief time, get to notice a little more of it. That is enough to make life feel extraordinary. Not because we have solved the universe. Far from it. Dark matter remains one of the greatest unsolved mysteries in science. We still do not know exactly what it is. We infer it through gravity. We model its effects. We build detectors. We test hypotheses. We rule things out. We refine the picture. But the substance itself, the deeper identity of whatever is forming this immense hidden scaffold, remains elusive. And strangely, that mystery adds to the beauty rather than subtracting from it. Because a solved universe might be a less enchanting one. Not a false enchantment, not an escape from truth, but the real enchantment of standing inside a world that still exceeds us. There is something healthy for the human mind in knowing that the cosmos remains larger than our categories. That even after all the mathematics, the telescopes, the data, the centuries of careful thought, we can still arrive at the edge of what we know and find ourselves facing something immense and dark and real and not yet fully understood. That is not emptiness. That is intellectual wonder. And wonder is one of the gentlest states the mind can enter. It is alert, but not agitated. It is open, but not afraid. It allows uncertainty without panic. It lets the universe remain big. Dark matter encourages that kind of wonder. It says, here is a galaxy you thought you knew. And here is the deeper hidden version of it. Here is a night sky you thought was full of stars. And here is the unseen structure holding those stars together. Here is a home you thought was visible. And here is the part of home no eye could naturally detect. That is a beautiful thing to be told by reality. There is also, I think, a subtle comfort in the fact that we are held by something we do not feel. The Earth's gravity holds us to the ground every second, and because it is constant, we barely notice it. The Milky Way's dark halo holds the galaxy together at a scale so vast that we cannot sense it directly at all. And yet it is there, part of the great background support of existence. The universe, in that sense, is full of unseen holding. Gravity itself is unseen. Dark matter is unseen. The structure of the galaxy is mostly unseen. And yet all around us are visible consequences of invisible order. Maybe that is why the cosmos can feel peaceful to contemplate. Underneath the apparent chaos, there are patterns. Motions are not random. Galaxies do not simply drift without meaning. There is architecture. There is relationship. There is hidden order beneath visible beauty. That does not mean the universe is safe in a human moral sense. It is not built for our comfort. But it does mean the universe is not merely scattered. It has coherence. And coherence is deeply calming. The Milky Way, with its vast dark halo, becomes a symbol of that coherence. A galaxy that is more than it appears. A visible beauty resting inside an invisible framework. A reminder that what holds things together is not always obvious at first glance. If this kind of slow exploration helps you unwind, you can gently subscribe and return whenever you want another quiet journey through the universe. And if you'd like, leave a comment about where in the world you're listening from tonight. There is something lovely in imagining listeners in different cities, different time zones, different corners of Earth, all resting inside the same hidden galactic halo, all carried together by the same larger home. And so now, after all of this, we return to the beginning in a new way. At the start, the Milky Way may have felt like a familiar thing, a beautiful band of stars, a known cosmic home. Vast, yes, but still understandable in outline. Then the clues began. The outer stars moving too fast. The missing mass. The flat rotation curves. The need for hidden support. The emergence of the dark halo. The widening scale. The reach into intergalactic space. The larger cosmic neighborhood. The coming meeting with Andromeda. The realization that our galaxy is not merely a shining disk, but a great invisible domain with a shining disk near its center. Now the Milky Way feels different, not less beautiful, more beautiful, because it is deeper, because it is stranger, because it contains, hidden inside the idea of home, a mystery vast enough to keep the mind tender and open. When you look up at the Milky Way now, or even just imagine it with your eyes closed, perhaps you can hold both versions at once. The visible one and the hidden one. The pale river of stars and the enormous dark halo surrounding it. The glowing city and the invisible country around it. The light and the weight. The thing we notice and the thing that does most of the holding. That double vision may be the real gift of this story. Not simply learning a fact about dark matter, but learning to see more than one layer of reality at a time. To understand that the obvious is not always the whole. To feel that the universe is larger, quieter, and more structurally beautiful than it first appears. And maybe, just maybe, that helps with sleep too. Because sleep is also a surrender to what we cannot fully control. A softening of the need to hold everything consciously. A trust that there are deeper processes carrying us through the night. In a strange cosmic way, the dark halo around our galaxy feels almost like that. A silent carrying structure. Unseen, but real. Vast, but gentle in its steadiness. Always there, whether we notice it or not. So as this part comes to a close, let the image settle. Above the Earth, beyond the clouds and the orbiting satellites, beyond the moon, beyond the sun's local neighborhood, the Milky Way turns in slow silence. Its bright disk glows with hundreds of billions of stars. And around that disk, extending far beyond sight, lies a vast halo of unseen matter, the greater body of the galaxy, the hidden structure that holds so much of it together. We live inside that. We always have. And though we cannot see it directly, it is part of what made our galaxy possible, part of what has carried our world through the dark for billions of years. That is what it means. It means home is larger than light. It means reality is deeper than appearance. It means the universe still contains secrets big enough to humble us and quiet enough to comfort us. And it means that tonight, wherever you are, however your day has gone, whatever small worries followed you into the dark, you are resting inside something immense and ancient and quietly real. A hidden halo. A galaxy beyond its glow. A home inside the unseen.